Very good evening to everyone. So welcome back to another session on GATE Champions series in electrical machines subject. So I hope the live is clear. Okay. So let me check once. Okay. So from my end, everything is clear. The live is started. The streaming has been started and the signal was also good. So any issues with respect to sound or clarity, please let me know in the chat box. Okay. Any doubts, please keep posting in the chat box so that once the session is completed, I will try to give reply to each and every question. Okay. All right. So this is synchronous machines. Okay. A quick review session. And I divided this subject into two parts basically. Okay. Because it is not possible to cover everything in a single lecture. So I divided synchronous machines into two parts. So in the first part, I'll discuss about the basics, also about the construction part of a synchronous machine, armature reaction, equivalent circuit, phasor diagrams, and voltage regulation, characteristics, and power flow equations mainly. Okay. So in the second part of the subject, I'll be discussing about parallel operation, synchronization of alternator with infinite bus bar, V and inverted V curves, and load characteristics of both generator as well as motor. Okay. And this particular session, and we are running this champion series from a long period of time. Okay. Especially targeting the upcoming GATE 25 examination related to electrical engineering students. Okay. All right. So this session, as I said, it's a quick review session and very much helpful for those students who wanted to revise this subject very quickly. Okay. And just to follow my lecture so that you will be able to recapitulate what you already studied in your preparation. Okay. Like what are the formulas, okay, how to draw phasor diagrams, okay, and understanding the concepts in a quick manner. Okay. All right. So without getting late, let us start the session. Okay. Just a moment, guys. I'll be back. All right, so let's start the session today. Okay, see, normally while we are studying about synchronous machine subject, normally in classroom, so we use it to study complete details of generators initially, and later we use it to study about synchronous motors. Okay, but during the revision process, you should not study generators and motors separately. We have to study them together. Okay, that means what is the EMF equation of generator? At the same moment, what is the EMF equation of motor? What about the phasor diagram of generator? Phasor diagram of motor, because there will be very minor difference between generator and motor. So reviewing both of them together will give a lot of clarity, and so that you can avoid confusions while solving numerical questions. Okay, all right. But during normal classes or during normal preparation, we use it to discuss generators first, without discussing anything about motors, and later we will discuss about motors. Okay, all right. So first thing first, what is the difference between a generating machine and a motoring machine? Yes, we all know that generator is nothing but any generator. It may be DC generator or AC generator. Generator is a machine which converts mechanical form of energy to electrical form of energy, and a motor is a machine which converts electrical form of energy to mechanical form of energy. See, when I said power or energy, it's all about real power, guys. Okay, so this mechanical power is the active mechanical power, and this is active electrical power. So I have shown you only the active power flow, okay, from input domain to output domain. Whereas reactive power flow, it can be generated by the machine, or it can be absorbed by the machine, or it may be neither generation nor absorption. It all depends upon the type of excitation. We will see that later. Okay. Now what motor will do? It will convert the real electrical power or active electrical power to active mechanical power. Remember, mechanical power means it's only active component, guys. There is nothing called reactive part of mechanical power, because mechanical power means it's the real power. Understand? Okay, it's the work done, therefore it's a real quantity. Whereas in electrical power, we will be having real part as well as imaginary part. Okay, so whatever I have shown you right now here, it's about active power flow only. So generator will convert active mechanical power to active electrical power. Motor will convert active electrical power to active mechanical power. Okay, interesting thing is, construction wise, both machines are going to be absolutely same. That means we can operate the same machine as a generator as well as motor. Okay, there is absolutely no difference. All right. Okay. Now, what is the basic operating principle of synchronous generator? As I have written very clearly, synchronous generator will work based on Faraday's law of electromagnetic induction. Okay, I said very clearly, Faraday's law of electromagnetic induction. In fact, DC generator will also work on the same principle. And what Faraday said, whenever a conductor is moving in a time invariant magnetic field, this is very important. Whenever you physically move a conductor in a time invariant magnetic field, then that conductor will experience changes in flux linkages. This is important, so that an EMF will be induced across that conductor. Okay, and according to Faraday's law, the magnitude of that induced EMF is equal to BLV sine theta. Okay, BLV sine theta. And here theta is the angle between flux lines and conductor movement. Okay, suppose if the angle is 90 degrees, maximum EMF will be induced. If the angle is 0 degrees or 180 degrees, EMF cannot be induced. This is what Faraday's law says that. And the interesting point every one of you have to understand here is, what type of magnetic field we need? Time invariant magnetic field. First of all, what is mean by time invariant field? Okay, time invariant field means the magnetic field which is constant with respect to time. Suppose if I take time on x-axis and flux or flux density on y-axis, it will be a constant value. With respect to time, the magnetic flux is constant. And we know what is the formula for flux. All of us know, right? In the earlier champion series session, I discussed about transformers. There I told you the formula for flux very clearly. Flux is equal to MMF divided by reluctance. Okay, MMF divided by reluctance. And what is the formula for MMF? Number of turns into current divided by reluctance of the magnetic path. Now, according to this relation, I can write the flux is directly proportional to current. Okay, so flux is directly proportional to current. And if you want time invariant flux, that means indirectly DC flux, you need to excite the magnetic system using DC current. Okay, therefore, in case of a synchronous machine, the magnetic field system is always excited using DC current. And remember, same thing is true even for DC generator also. Even in a DC generator also, we need time invariant magnetic field. Therefore, we have to excite the field system using DC current. Okay, so let me verify the connection once. Is the live running smoothly? Yes, I think it was working well. Okay, all right, fine. So both in a DC machine and a synchronous machine, the field system must be excited using a DC current. Then only time invariant magnetic field will be created. So I can write that point. Yes, in DC machine and synchronous machine, okay, the field winding or field system, the field system is excited using DC supply. Okay, yes, you can obtain the similar type of magnetic field using permanent magnets also. We know that permanent magnet means the flux developed by that magnet will be constant with respect to time. But the disadvantage with permanent magnet is you can't control the magnitude of the flux. You can't increase it, you can't decrease it. Therefore, excitation will be constant. But if you have electromagnets where you are using a DC current supply, you can increase the magnetic flux value or decrease the flux value based on the requirement. That means excitation can be controlled. That's why all practical generators will normally have a variable excitation by using a DC supply. Suppose if the machine is a very small machine, you don't need variable excitation, then you can even go for with permanent magnets as well. Okay, all right. So this is time invariant field. Now the greatest question is, most of the students will have a common doubt that, sir, if the flux is DC flux, how can AC voltage can be generated by alternator? Okay, so to understand that, I will consider a simple magnetic system here. Okay, consider we have a magnetic system having two poles. Let's say we have a north pole here and south pole here. Important thing is I am exciting this field system with DC supply. Therefore, the flux is time invariant. Okay, all right. Now, in this magnetic field, imagine a conductor was rotating with the help of a prime mover. Okay, yes, we are using mechanical power as input. That mechanical power can be obtained from a prime mover like a turbine. It may be, a steam turbine or water turbine or wind turbine, anything it may be. So this is position 4. Finally, this is position 5. You all observe that I started at this position, position 1, and I came to that same position. That means one revolution I am considering. Now, in these positions, we need to find out the magnitude of the induced EMF. Okay. What is the formula for induced EMF? As I mentioned, according to Faraday's law, the induced EMF is equal to BLV sine theta, where B is flux density, L is length of the conductor, V is velocity of the conductor, and theta is the most important part, that is the angle between magnetic field and conductor movement. Okay, now let us look at that. Look at position number 1 first. As I said, conductor is rotating in clockwise direction. Clockwise direction means, can I say at position number 1, conductor was moving to right side? Yes. This is the direction of velocity. All right or not? So conductor was driven in clockwise direction. It was moving to right side. What about magnetic field? Magnetic field will always flow from north pole to south pole. Therefore, magnetic field is horizontal. The velocity of the conductor is also horizontal. What is the angle between the two? 0. And if you keep that 0 degrees here, what is sine 0 degrees? 0. That means EMF cannot be induced. Therefore, at position number 1, the induced EMF is equal to 0. Got it? Okay. Now look at position number 2. Clockwise movement means, can I say conductor was moving in a downward direction at a velocity V? Now, what is the direction of magnetic field? Magnetic field is always from north pole to south pole. Conductor was moving in downward direction. So, what is the angle between flux lines and conductor movement? 90 degrees. And if you use that 90 degrees here, what is sine 90? Maximum. Therefore, at position number 2, the induced EMF is a maximum value. Clear? Okay. Next, position 3. Clockwise movement. Therefore, this is the velocity of the conductor. Magnetic field is from north pole to south pole. Therefore, the angle between flux line and conductor movement was 180 degrees. What is sine 180? 0. So, therefore, at position 3, the induced EMF is again 0. Next, look at position number 4. Clockwise movement. That means conductor 4 was moving in upward direction. Magnetic field is from north pole to south pole. Therefore, the angle between the two is 90 degrees. What is sine 90? Maximum. So, at position number 4, the induced EMF is maximum. Okay. Keep posting your questions in the chat box. Okay. Once the session is completed, I will go through each and every question and I will give you proper reply. Okay. During the session, I may not be able to, answer your questions, but after the session, I will answer all your questions. Okay. Keep posting. Okay. And also share this class with your friends. Okay. Watch it completely so that you can revise at least 50% of synchronous machines without any effort. Okay. In the next part, I will revise the remaining 50% portion. Okay. All right. Fine. Now let us focus on fifth position. Can I say fifth position or first position? Both are same. Therefore, at position 5, the induced EMF is again 0. Therefore, after one complete revolution, I found all the maximum and 0 EMF positions, guys. Okay. Yes. How do you find out the magnitude of the EMF? Faraday's law. According to Faraday's law, we found the magnitude of the induced EMF. Now the next question is, once you know the magnitude of induced EMF, how to find out polarity of the induced EMF? Okay, yes, very simple. The polarity of induced EMF can be identified using Fleming's right hand rule. Fleming's right hand rule. Okay, so Fleming's right hand rule will not give you magnitude of EMF. Instead, it will offer you the polarity of the induced EMF. So I hope most of you might have learned about Fleming's right hand rule. According to that, the first 3 fingers of the right hand must be placed in a mutual perpendicular direction. Okay, this is a thumb, this is a point finger, this is the central finger of the right hand. Okay, so here thumb indicates the direction of conductor movement, point finger will indicate the direction of magnetic field, and the central finger of the right hand will indicate the polarity of the induced EMF. Got it? Now let us practice this Fleming's right hand rule here so that we will be able to identify the polarity of the induced EMF as well. Okay, now see, at position 1 and position 3, already the induced EMF is 0. Therefore, no need to find out its polarity. But at position 2 and position 4, maximum EMF is there. Let us find out the polarity. Now see, at position 2, if I do it, conductor was moving in downward direction with the help of prime mover. Yes, that is the thumb. Thumb is showing the direction of conductor movement. Magnetic field is always from north pole to south pole. See, my point finger was showing a magnetic field. Now what my central finger was showing, is it not showing out of the plane? Yes, coming out of the board. So that is out of the plane represented with a dot polarity. Okay. Next, coming to position number 4, conductor was moving in upward direction. See, my thumb is showing upward direction. Magnetic field is always from north pole to south pole. Now my central finger was showing into the plane. That is a cross polarity. Therefore, if you clearly observe this diagram, position 2 and position 4 are having opposite polarities or same polarity, exactly opposite polarities. This is a dot coming out of the plane. This is a cross going into the plane. Now tell me mathematically how to show two opposite polarities. Okay, mathematically you can't write cross and dot, right? Okay, so mathematically I can show two opposite polarities using plus and minus symbols. Therefore, in case if I assume this dot is a positive polarity, then cross becomes negative polarity. Or if I assume cross is a positive polarity, dot becomes negative polarity. Of course, you can't assume both positive or both negative. So what I am assuming here is that I am assuming, cross is a positive polarity, therefore dot is automatically negative polarity. Clear? So that means at position 4 we have positive EMF. At position 2 we have negative EMF. Now let us draw the waveform for the induced EMF. Okay, so see, I am taking the position of the conductor, that is what we call it as space position of the conductor on x-axis, and I am taking the EMF on y-axis, and we have how many positions, guys? Overall 5 positions are there. Let us say this is position 1, 2, 3, 4 and 5. Yes, at position 1 and 3 the EMF is 0. At position 1 EMF is 0. Position 2 negative maximum. See, this is negative maximum. Position 3 EMF is 0. Position 4 positive maximum. Position 5 EMF is 0. And if I combine all these points, yes, what is your observation? Is it not an alternating voltage? Yes, definitely. Okay, practically it is alternating voltage, but you don't get pure sinusoidal waveform. I repeat, practically the waveform shape cannot be pure sinusoidal. Okay, so some kind of non-sinusoidal nature is involved, which creates harmonics in the machine, and we have various techniques to mitigate those harmonics. Okay, Just ideally, I am assuming it is a pure sinusoidal wave, ideally. Okay. But one thing is very clear, even though the magnetic field is a time invariant type, but when you rotate a conductor in that magnetic field, definitely alternating voltage is inducing. Okay, a very simple thing. When you rotate the conductor, okay, in a clockwise or anti-clockwise direction, for a certain period of time, the conductor is under south pole. Next half period, the conductor is under north pole. Again, south pole, north pole, south pole, north pole. And we know north and south means two opposite polarities. Therefore, when you revolve the conductor in this magnetic field, the conductor is facing alternating magnetization. Okay, for few seconds south pole location, next few seconds north pole, again south, again north. So negative, positive, negative, positive. That is how alternating voltage will be induced even though magnetic field is time invariant. Okay, hope your doubt is clear now. So even though magnetic field is time invariant, an alternating voltage is getting induced across every conductor when it is driven in that time invariant magnetic field. Okay, alternating voltage is fine, but the requirement is not only alternating voltage, it must be sinusoidal. If it is a sinusoidal, then only you can say the total harmonic distortion will be very, very low, and that will be reliable and stable in power system. Okay, so but as I said, practically it is impossible to make voltage purely sinusoidal. Harmonics will always be involved, and to reduce those harmonics, we have various techniques like short pitch winding, skewing of the conductors, okay, using fractional slot pitch coils rather than integral slot pitch coils, distribution of the winding. By using all these techniques, we can reduce the harmonics in the machine and we can make output voltage almost like a pure sinusoidal waveform. Correct? Okay. And now, next question is, yes, it is a sinusoidally, or you can say alternating EMF, that is fine. Then what is the frequency of that induced EMF? Yes. I'm not proving that formula, but we know the frequency of induced EMF is equal to P into N divided by 120 Hertz. Okay, P into N divided by 120 Hertz. Okay, just a moment. Okay, so here P is representing number of poles, and N is representing the speed, rotor speed of the rotor in RPM, okay, revolutions per minute. And we know once machine construction is completed, can I say number of poles will be constant? Therefore, the frequency of induced EMF will only depend upon the speed at which the rotor was rotating. Therefore, I can write frequency is directly proportional to NR, that is the speed at which the rotor was rotating. And we know in power system, alternators are expected to generate voltage with constant frequency or variable frequency, constant frequency. Therefore, can I say frequency can be constant only when the speed of the machine is constant? Okay, just a moment. Yes, frequency will be constant only when we drive the rotor at a constant speed. Okay, therefore alternator is a machine which has to be rotated at a constant speed always, ideally. But practically speed will never be constant. Whenever load changes, speed is subjected to change. Of course, there will be turbine governor system again will act, damper winding will be there, synchronizing torque will be there to get the speed back to rated value. But ideally, I can say to keep the frequency constant, we have to keep the machine speed constant. Okay. Now we need to understand what is mean by synchronous speed in generator. Okay, what is mean by synchronous speed? We oftenly study about this particular quantity called as synchronous speed. Very simple. Synchronous speed is nothing but the rotor speed at which, I repeat, it is the rotor speed at which the generated EMF frequency is equal to infinite bus bar frequency. What is mean by bus bar frequency in power system? Is it not 50 Hz in India? Yes. Therefore, the rotor speed at which generated EMF frequency is equal to 50 Hz, that is what we call it as synchronous speed. First of all, what is the formula for frequency we have just seen? Frequency is equal to P into N divided by 120 Hz. From this, N is equal to 120 F by P. Alright. Now, I want 50 Hz frequency exactly. Okay. At what speed 50 Hz frequency is generated, that is what we call it as synchronous speed. So every rotor speed cannot be called as a synchronous speed. Synchronous speed means it is the speed of the rotor at which generated EMF frequency is equal to 50 Hz. That means generated EMF frequency must be equal to bus bar frequency. That is the speed we call it as synchronous speed. For example, find synchronous speed of a 6-pole alternator. I asked you a question of a 6-pole alternator. Okay. So what is the formula I just derived? Synchronous speed is equal to 120 F by P. But what is the frequency I must use? 50 Hz. Therefore, 120 into 50 Hz divided by 6 poles the machine has, and if you solve it, you will get 1000 RPM. Therefore, 1000 RPM is the synchronous speed for the given generator. Okay. What if I rotate the machine at 900 RPM only? Or what if I rotate the machine at 1100 RPM? Then the frequency of induced EMF cannot be equal to 50 Hz. We'll get a different value. Okay. Asynchronous speed. We call that speed as asynchronous speed then. Okay. So finally, an alternator is expected to generate a constant frequency voltage. Therefore, ideally, the speed of the alternator must be constant. At least I can say at a steady state condition, the speed of the alternator must be constant, and that too synchronous speed. Okay. All right. Now, let us quickly try to understand how an alternator will be working. Okay. How can an alternator will generate balanced 3-phase output voltage. Okay. Generally, majority of the power system, generation, transmission and distribution will happen in 3-phase format. Therefore, our alternators are also expected to generate balanced 3-phase voltages. Okay. First of all, what is mean by balanced 3-phase voltages? Yes. First of all, 3 phases are there, A, B, C. Balanced 3-phase voltages means all the 3-phase voltages must be equal in magnitude. That means their RMS values must be equal. Also, they must have 120 degrees phase angle difference. Then only I can say those voltages are balanced in nature. Clear? Yes. So, in order to generate balanced output voltages from synchronous generator, what we are going to do? Okay. First thing first, you need to understand synchronous machine will have 2 windings. Okay. One is field winding, and the second one is armature winding. As the name of the winding itself is going to tell you, field winding is used in order to generate field flux in the air gap of the machine. Okay. Its purpose is not to generate the power or voltage or current. It is just to develop magnetic field in the air gap. And armature winding is the one where the actual EMF will be induced utilizing the field flux. Okay. So, this field winding will generate a flux. We call it as a field flux. That field flux will induce an EMF in armature winding. Therefore, output voltage of a synchronous generator means it is the voltage from which winding? Armature winding. Okay. And in case of a synchronous generator, this armature winding will be on stator part of the machine. Armature winding will be on stator part of the machine, and the field winding will be on rotor part of the machine. Okay. And if you discuss the same thing in a DC generator, exactly opposite. In a DC generator, armature winding will be on rotor, field winding will be on stator. Okay, that we will study in DC machines. But right now, in a synchronous machine, you need to understand that field winding will be on rotor, armature winding will be on stator. And as I said, the output voltage of the generator is from which winding? Armature winding. And I told you already, we need balanced three-phase output voltages. Okay. So therefore, the stator must have balanced three-phase distributed winding. Okay. Let's see that. Okay. So this is the stator part of the machine, a circular cross section, the cross section of the stator. And I wanted to take three-phase winding. Okay. So let's say this is phase A. A is here, A dash is here. Okay, and what is the angle between A and A? A and A dash, is it not 180 degrees? So that is what we call it as full pitch coil. Okay, a winding will have at least one turn. One turn means you need two conductors. Okay, these mean, basics I am not covering here. Okay, I hope you are at least known what is mean by coil, what is mean by turn, etc. So when I said one turn, minimum two conductors will be there. Okay, one conductor we will try to keep it under North Pole, the other conductor we will try to keep it under South Pole. And currently I am taking 180 degrees between these two conductors. That is what we call it as full pitch. But practically, to reduce harmonics, we will generally use short pitch, that we will consider little later. Okay, right. So this is where phase A winding started. Now next, phase B winding. Okay, so see that after exactly 120 degrees, see this is 180 degrees. After exactly 120 degrees, you have to wound phase B. And opposite side, we have B dash. Correct? So what is the angle between A and B if I ask you? That is 120 degrees. From here to here, if you calculate 120 degrees. This is what we call it as space angle. Okay, any physical angle that you are able to measure on the top of the machine, we call it as space angle. Now, if this is phase B, can I say phase C must be wounded after how many more degrees? 120 more degrees. Here comes phase C, exactly opposite we have C dash. So this is a three-phase balanced distributed winding on the stator part of the machine, and we call that winding as armature winding. Okay, when I said three-phase winding, can I say we can connect this three-phase winding in two formats? One is star connection, another one is delta connection. Whether it is a star or delta, whatever may be the connection, how many terminals will come as output? Three terminals. Okay, so line A, line B, and line C. These are the three output terminals. Okay, but generally we will prefer stator always a star connection. Okay, generally armature winding is a Y connection. Why armature winding is generally a Y connection? From the machine's point of view, there are two advantages of a star connection. Okay, two advantages. First advantage is, if each winding was able to generate a voltage of V, then the line voltage will become root 3 into V, which is 73.2% more than phase voltage. Okay, because we know root 3 is nothing but 1.732. Therefore, line voltage will be 73.2% more than phase voltage. Whereas, if you consider a delta connection, let's say, suppose if you make armature winding as a delta connection, if a phase voltage is V, that means if voltage across every winding is V, then the line voltage is also equal to V only. Okay, so in order to generate higher output line voltages, generally we will prefer star connected winding. This is one reason. Now, second reason is, as I told you, ideally we are expecting pure sinusoidal voltages, but practically pure sinusoidal voltages are not possible. Harmonics are always involved. And one of the most dominant harmonic is third harmonic. We know the most fundamental working component is first harmonic, right? After first harmonic, what is the next most effective? Third harmonic. Okay, let us assume that every phase winding has fundamental voltage as well as third harmonic voltage. Okay, let's say this particular phase A has two voltages in it. One is fundamental voltage V1, another one is third harmonic voltage V3. Of course, fifth and seventh, ninth, etc. other higher order harmonics will also be there. But as I said, the dominant harmonic is third harmonic. Similarly, phase B also, let us say this is A, this is B, this is C. Similarly, phase B also will have fundamental voltage as well as a third harmonic voltage. Phase C will also have fundamental voltage and third harmonic voltage. Now see what is the advantage of a star connection. Let me remove here. Okay, so when the phase winding has fundamental voltage as well as third harmonic voltage, let me calculate the line voltage. VAB, can I call it as line voltage? Yes. Is it not VA minus VB? That is a phase A voltage minus a phase B voltage? Yes. What are the two voltages we have in phase A? Fundamental voltage V1, that one is representing first harmonic. Let us say this is at an angle 0. And third harmonic voltage V3, I don't know at what angle third harmonic voltage is in. You take any random angle, I am taking 0 degrees. Okay, minus, what about phase B? Yes, we know from phase A to phase B, 120 degrees phase angle difference will be there. Therefore, fundamental voltage will be at an angle minus 120. But third harmonic voltage remains at 0 degrees only. Why? Both third harmonic voltages are at the same angle. Why? Because third harmonic component belongs to zero sequence component. When it belongs to zero sequence component, all the three phase voltages are at the same phase or same phase angle. Therefore, if phase A third harmonic voltage is at an angle 0, phase B third harmonic voltage is also at an angle 0. Therefore, both will cancel each other because there is a minus sign in between. So the moment these two voltages cancels each other, then what is the remaining? V1 at an angle 0 minus V1 at an angle minus 120. When you solve it, you will get root 3 V1 at an angle plus 30 degrees. Okay, root 3 V1 at an angle plus 30 degrees. Therefore, finally, you see when you calculate the line voltage will have only V1 term or also V3 term? Only V1 term. Can I say V3 term cancels? Therefore, even though the phase voltages are having third harmonic EMF, when it comes to line voltage, third harmonic EMF is cancelled. So when I say harmonic voltage cancelled or neutralized, output voltage will be more sinusoidal or less sinusoidal? More sinusoidal, which is definitely an advantage. This is another reason why star connected windings are preferable, okay, rather than delta. Okay, there is one more reason, that is a protection point of view. You can make this neutral grounded using some neutral impedance, okay, and you can connect a relay there to protect the synchronous generator. That generally you will study in power system protection, okay. But from the machine's point of view, higher output line voltage is possible with star connection. Harmonic voltages can be neutralized, specifically third harmonic voltage, okay. Yes. Okay, that is one reason why stator winding is always star connected. Okay, fine. Now coming to rotor, as I told you, what is the rotor part of synchronous generator? Field winding. Okay. Yes, I hope the session was running smoothly. All right. Now let us consider the field circuit of the machine. As I told you, the field is on the rotor part of the machine. Okay, so let us consider, for example, this is how the rotor is given. A two-pole rotor I am considering. Okay, so we specifically call this rotor as a salient pole rotor, and there are two types, salient pole and cylindrical rotor, we will see. And this rotor will have a winding, we call it as a field winding. And in order to create a time invariant magnetic field, we will excite this field winding using DC supply. Let's say this is field voltage and the current is field current. And now based on the direction of current, you can estimate the direction of a field flux. Can I say the flux is in upward direction using right hand thumb rule? Yes. So therefore, this one will act like north pole, this one will act like south pole. Okay. And you see right now, from the diagram you can understand, you see conductor A is exactly under north pole. This is what we call it as direct axis of the machine. The one which is passing through the poles, we call it as polar axis or direct axis. Okay, and whenever conductor is along direct axis, maximum EMF can be induced. And one more thing, this is rotor part, right? Rotor means it has to be, it is rotating in nature. Who will rotate the rotor? Prime mover. Okay. So imagine the prime mover was rotating this rotor in clockwise direction at a synchronous speed. Okay. Now, right now, you can understand which conductors are under direct axis of the machine. Is it not A and A dash? Therefore, maximum EMF will be induced in phase A winding right now. Okay. So, see that right now, maximum EMF can be induced in phase A winding. Okay. So, let me try to draw that waveform. Okay. Here. So, let us say I'll be taking the space angle or time on x-axis and voltage on y-axis. Okay, this is the starting position and phase A voltage is maximum. Okay, this is phase A voltage waveform, and right now you see phase A voltage was maximum. Understand? And we know only alternating voltages will be induced. Why alternating voltages will induce? Even though the field is time invariant nature, we studied already, right or not? Okay. Now, what about phase B winding and phase C winding? Next, see this. The rotor is stationary or rotating? Rotating in nature. So if you rotate this rotor exactly 120 degrees, this north pole will come to this location and south pole will come to this location. When north is here, south is here, you can easily understand now phase B winding is under the direct axis. Okay. This is possible only if you rotate the rotor, guys. Okay. If you rotate the rotor exactly after 120 degrees, north pole was at B position, south pole was at B dash position. Now the direct axis is along phase B. That means phase B voltage will be maximum after 120 degrees. Okay, after 120 degrees, phase B voltage will be maximum. Let me use a different color. See, let's say from here to here, this is 120 degrees. Okay, just a moment. Just wait. I'm not good at diagrams. I hope you're able to understand. So, this is going to be phase B voltage. Okay, just a minute. Okay, this is phase B voltage. So from phase A to phase B, you can see there is 120 degrees phase angle difference. Now, currently north is here, south was here. What if I rotate the rotor by 120 degrees more? Then north pole will come to C, south pole will go to C dash. That means phase C winding is along direct axis. So maximum voltage will be now along phase C winding, that is after 120 more degrees. Okay, after 120 more degrees, you can understand phase C voltage will be maximum. Therefore, the point is from phase A to phase B to phase C, there is exactly 120 degrees phase angle difference is there. And what is the sequence of the output voltage? A, B, C. Okay. Now, what if I reverse the rotation of the machine? Suppose if I try to rotate this rotor in anti-clockwise direction, what will happen? Right now, phase A voltage is maximum, very fine. If I rotate this machine in anti-clockwise direction, after 120 degrees, north pole will come to C location, south pole will go to C dash location. Therefore, phase C voltage becomes maximum value. After one more 120 degrees, phase B voltage becomes maximum value. Therefore, the output sequence becomes A, C, B. Therefore, I can understand the output sequence of the voltages will depend upon the direction of rotation. It never depends upon the excitation. Okay, whether you give plus minus excitation or minus plus excitation, it doesn't matter. But the sequence, output voltage sequence will always depend upon the direction of rotation. If you rotate the machine in clockwise direction, ABC sequence is coming. If you rotate the machine in anti-clockwise direction, ACB sequence is coming. Okay, so important observation, output sequence will depend upon the direction of rotation. Clear? Okay, this is how practically a synchronous generator is working, a simple working principle. Understand? So the magnetic field must be time invariant. But when you rotate the rotor, alternating voltage will be induced in armature winding. Okay, remember, armature winding is stationary, the field winding is rotating. Clear? Okay. Now, let us try to understand the next important aspect in synchronous machine, field theory. To understand this field theory, I would like to consider synchronous generator first. Later, we can apply the same concept to synchronous motor. Okay, so let us consider a synchronous generator first. Okay, so consider this is the stator part of a given synchronous generator, and this stator has two conductors. Let us say this is A and A dash, that is phase A, and rotor is here. Let us say this is the rotor part of the machine. Okay, there are two poles in rotor. Let us say this is north pole and this is south pole. Remember, there will be a field winding, and we will excite this field winding using DC supply. This is a field voltage, this is a field current. Based on the direction of a field current, you can estimate the direction of a field flux. Okay, you can understand the field flux is in upward direction. Okay, let me anti-clockwise direction at a synchronous speed. This is my assumptions only. You can rotate the rotor in clockwise direction also, no problem. Okay, now can I say conductor A and A dash are along direct axis of the machine, the axis which is passing through the poles. So as the two conductors are along direct axis, maximum EMF will be induced in those two conductors. So question is how to identify the direction of the direction of induced EMF. Okay, yes, Fleming's right hand rule. According to Fleming's right hand rule, thumb will represent the direction of a conductor movement with respect to field. Point finger will indicate magnetic field direction. My central finger of the right hand represents the polarity of the induced EMF. But if you look at the diagram carefully, the conductors are rotating or conductors are stationary? Yes, the two conductors are stationary because they are on the stator part. But magnetic field is rotating in nature. In which direction the magnetic field is rotating? Anti-clockwise direction. If a magnetic field is rotating in anti-clockwise direction, is it equivalent to conductors rotating in clockwise direction? That is what we call it as relative movement. Okay, one simple practical example. Suppose you are moving on a bike. Okay, imagine your bike is moving in forward direction at a certain speed, and you observe the road while you are traveling on the bike. You just observe the road and trees outside your vehicle. How those objects are looking like? Yes, they looks like moving opposite to your vehicle. Am I correct? But what is the fact? The fact is the road, the trees, the buildings, they are all stationary. Your bike is moving in forward direction. But with respect to your bike, if you look at those stationary objects, they look like moving opposite to your vehicle. That is what we call it as a relative movement. Understand? If you apply the same concept here, the field is rotating in anti-clockwise direction. That is equivalent to this conductors rotating in clockwise direction. Relative movement. So if I take the relative movement of this conductor, it looks like rotating in clockwise direction. Clockwise direction means to the right side. Yes, conductor A was moving to right side. Magnetic field is in upward direction. You can see north pole is emitting the flux, upward direction. Now my central finger was showing out of the plane, okay, which is a dot polarity. So therefore, in a conductor A, the polarity of induced EMF is a dot polarity. And therefore, in A dash, the polarity of induced EMF is a cross polarity. Okay, this is the maximum EMF. Okay, now once EMF is induced, can I say immediately current will be generated if the load is connected? Imagine you connected some load on the armature winding, so immediately current started to generate. Okay, so therefore this dot polarity EMF will generate armature current as a dot polarity. This cross polarity conductor will generate a current with cross polarity. Okay, so EMF and current polarities are same because the machine is a generator. Okay, now these two conductors are normal conductors or current carrying conductors. Therefore they will create one more flux in the machine known as armature flux. So far there is only one flux in the machine, field flux, created by this field winding. That is what we call it as a rotor field. But now, due to these current carrying conductors, one more field is created. We call it as armature field. Now the question is how to identify the direction of armature field? Yes, using right hand thumb rule. You see, this conductor was carrying the current into the plane. See, my four fingers are going into the plane. This conductor was carrying the current out of the plane. So my thumb is representing the direction of a stator magnetic field. Okay. Yes. So this is the direction of stator magnetic field. Okay. Clear? Stator field or armature field, any word is same. Now the next question is coming to the rotations. Okay. Yes. See, rotor is stationary or rotor is rotating? Rotor is rotating in anti-clockwise direction. If rotor was rotating in anti-clockwise direction, this north and south poles will also rotate along with rotor. That means indirectly the rotor field is rotating in anti-clockwise direction at synchronous speed. Clear? Okay, very simple. Rotor was rotating, that's why rotor field is also rotating. What about stator field? Stator was rotating or stator is stationary? Stator is stationary. Yes or not? Stator winding, stator conductors, everything stationary. Now, even though stator is stationary, stator field will be rotating in the same direction with a synchronous speed. This is where the question will come. Why stator field is rotating even though stator winding is stationary? Yes, the reason is distribution winding. We know stator winding is a concentrated winding or distributed winding. It is a three-phase distributed winding. Also, it is carrying AC current or DC current? AC current. Why? Because the induced voltages are alternating voltages. Therefore, the current is also going to be alternating current. And remember, whenever distributed winding carrying AC current through it will create rotating magnetic field. Okay. Concentrated winding cannot create rotating magnetic field. Best example, transformer. But distributed winding, that too carrying AC current, will create rotating magnetic field. Therefore, even though stator winding is stationary, the stator field is rotating. With how much speed? Synchronous speed. Now, how many magnetic fields are available in the machine? Two magnetic fields are available. One is a rotor field, another one is stator field. Therefore, what is the resultant magnetic field? Is it not a vectorial summation of these two? So therefore, by using parallelogram law, if I add these two magnetic fields, we will get the resultant magnetic field. We call it as air gap field. Okay, resultant magnetic field or air gap field. Now see, if rotor field and stator field both are rotating, automatically this air gap field is also rotating at synchronous speed. So the observations are very simple. Rotor field is rotating at a synchronous speed. Stator field is rotating at a synchronous speed, and air gap field is also rotating at a synchronous speed. Therefore, if I ask you what is the relative speed among all these three magnetic fields, the answer will be 0. Why? Because all fields are rotating in the same direction with same speed. But if I ask you one more question, which field was leading and which field was lagging? Is it not rotor field leading air gap field in the direction of rotation, and stator field is following air gap field, that means lagging? Yes. So in a synchronous generator, rotor field will lead air gap field. Okay, and stator field will lag air gap field. Stator field will lag air gap field. Okay, and all fields are rotating at synchronous speed. So what if I ask you what is the speed of rotor field with respect to rotor? See, the moment I use the word called with respect to, that means relative speed. These kind of theoretical questions are very important, especially for 1 mark model, also MSQ model, multiple select questions. I may give you 4 options. In synchronous generator, which of the following statements are correct? Option A, the relative speed between rotor field and rotor is 0. Is it correct statement or wrong statement? Correct. Why? Because rotor field is rotating with synchronous speed. Rotor was also rotating with synchronous speed. Therefore, the relative speed is 0. Option B. The speed of rotor field with respect to stator field is ns rpm. That is wrong. Why? Because rotor field and stator field both are rotating at a synchronous speed. Therefore, their relative speed should be 0, right? What if I give you another statement? The speed of stator field with respect to stator is ns rpm. Yes, that is correct. Why? Because stator field is rotating with ns rpm, but stator is stationary. Stator means stator core, stator winding, etc. It is stationary. Therefore, the relative speed is ns rpm. That is correct. Okay. Likewise, you can expect a few questions from the field theory diagram. Now, I wanted to discuss the same concept in synchronous motor. What will happen? Everything will be same except current direction. We all know that synchronous generator means it is a machine which generates armature current, and synchronous motor means it is a machine which will absorb armature current. Therefore, you reverse armature current direction, you will get the field diagram of the synchronous motor. Okay, I need to draw it, but as it is a quick review session, I am not drawing it, but I hope you can understand. So what happens? Everything remains same, but here current becomes cross polarity. Here current becomes dot polarity. Therefore, you can understand if this is cross and if this is dot, the stator magnetic field will be in this direction, right? So you can understand that stator field will be in this direction. Okay, rotating at synchronous speed. Rotor field will be at the same location. This is rotor field rotating at a synchronous speed. Now you tell me which field was leading and which field was lagging. Stator field is leading, rotor field is lagging. Exactly opposite to generator. Okay, so I hope you can easily understand that, because the only difference is the direction of current reverses. That's all. Okay, so let me eliminate these things. So I request all of you, please try to understand the field theory of a synchronous motor as well. Fine. Okay, this is generator. Motor means exactly current reverses, especially armature current. Okay, armature current reverses, so that you can understand. Okay, so this is about the field theory in case of synchronous machine. Now let us move to construction part of alternator. Okay, so when it comes to construction, synchronous machine is divided into two types based on the design of rotor magnetic circuit. One is salient pole rotor type, another one cylindrical rotor type. Okay, now in these two machines, the stator design will be same, only the rotor design will have the difference. Okay, so first of all, how does stator looks like? Stator will be having a circular cross section. Okay, cylindrical structure. The overall structure looks like a cylindrical structure, and it is high permeability ferromagnetic material. Generally, we will use a silicon steel. Okay, and this stator will have a number of slots on it. Okay, so I am not drawing the complete diagram. I hope you have the basic idea. Okay, so number of slots will be there on the stator part. On these slots, the conductors will be placed. The armature conductors are going to be placed. All right, and the conductors will also have a length equal to stator core. Okay, like this. So number of conductors will be there, and finally all these conductors are connected together to form a three-phase balanced distributed winding. Okay, so this is how the stator looks like. Okay, so and this is the same stator we will use even in induction motor also. The stator design is common in synchronous machine as well as induction machine. Even in induction machine also, stator will have a balanced three-phase distributed winding, and a synchronous machine also has balanced three-phase distributed winding. But the rotor designs are going to be different: salient pole rotor and cylindrical rotor. We will see the difference between the two. Okay, so what does salient pole rotor looks like? So imagine once again, this is the stator part of the machine, and saliency means projection. Okay, according to English meaning, saliency means it's a projected nature, and salient pole rotor means the rotor will have some projected type of poles. Okay, so imagine this is the rotor part of the machine. Okay, I am drawing a 2-pole rotor right now. You can even select a 4-pole or 6-pole or any number of poles. This is how the rotor looks like. So such type of pole shoes are known. Okay, we call charm uniquely at the center of the pole. The air gap is minimum, and if you go towards the end of the pole, what is happening to air gap length between stator and rotor? Increasing, right? So that is chamfered pole shoe nature. So the air gap is non-uniform between stator and rotor, and typically this is known as direct axis of the machine. And along direct axis, air gap is minimum or maximum? Minimum. Very less air gap is there. And perpendicular to direct axis, we have a quadrature axis, and there is a more air gap between stator and rotor. This is higher air gap. So direct axis has a minimum air gap, quadrature axis has a maximum air gap length. So salient pole rotor offers non-uniform air gap length between stator and rotor. Now, what is the advantage of this non-uniform air gap length? Very simple. Because of this non-uniform air gap length, the magnetic flux is distributed in a sinusoidal manner. If I take field flux on y-axis and the space position on x-axis, that means with respect to space angle, you see this is a quadrature axis, right? So maximum air gap length is there. When air gap length is maximum, reluctance is maximum, therefore the effect of magnetic flux is minimum, almost zero, right? Next, when you go to direct axis position, air gap length is minimum, reluctance is minimum, so flux will be maximum. So exactly at direct axis, this is quadrature axis position, this is the direct axis position. Along direct axis position, the magnetic flux is maximum. Okay, again when you go to this quadrature axis position, again air gap length is maximum, reluctance is maximum, therefore flux will be minimum. Again at quadrature axis position, the flux is minimum. So if you draw a curve, it is almost like a sinusoidal wave. I said almost, not exactly sinusoidal. Okay, so the non-uniform air gap length will create almost like a sinusoidal flux waveform, but still harmonics are involved. You cannot get 100% sinusoidal nature. Harmonics are always involved. To minimize those harmonics, we will use short pitch winding and other techniques. Okay, anyway, so this is the advantage of a non-sinusoidal waveform here right now in salient pole machine. But what is the disadvantage? The disadvantage is because the air gap is non-uniform in nature, when you try to rotate this rotor at very high speed, centripetal forces may crush the rotor. Mechanically, the rotor may damage because the air gap is non-uniform. So when you try to rotate this rotor at higher speeds, then the centripetal forces becomes very large and they may damage the rotor physically. That is why salient pole rotor is used only for low speed prime mover applications. Low speed applications only. Low speed applications. Okay. Best example, water turbines. Water turbines means hydel power plants. Water turbines are generally designed to give higher efficiency at lower speed. Therefore, for low speed applications, we will use these salient pole rotor type synchronous machines. Okay, and physically if you see, they are larger in cross section and less in axial length. Okay, larger cross sectional area and less axial length. The length of the core is less, but cross-sectional area of the machine is large. Okay, so this is about salient pole rotor type synchronous generator. Okay, next important observation is damper winding effect on salient pole rotor. Why damper windings are used? Where do we place damper windings? See, damper windings will serve three purposes in case of synchronous machines. Okay, first one, they will reduce because of damper winding, oscillations can be reduced during hunting phenomena. Okay, so minimizing the oscillations during hunting process. This is the first advantage of damper winding. Second advantage is it provides starting torque. It provides starting torque in synchronous motor. Generally, inherently synchronous motor is not a self-starting motor. In order to make it as a self-starting motor, we will use damper winding. Okay, damper winding can create starting torque for synchronous motor. Also, it can suppress, okay, it suppresses the harmonic torques during unbalanced loading conditions. This you will study in power system majorly. Okay, in power system stability concepts, whenever the load is unbalanced, negative sequence currents will be generated by the armature winding. Those negative sequence currents will create harmonic voltages within the rotor. In order to suppress them, damper winding will be helpful. Okay, so this is power system stability concept. Okay, but coming to the machines concept, hunting process can be minimized, okay, because of the damper winding, and you can also create a starting torque in synchronous motor. Next question, where do we locate these damper windings? Very simple. Damper winding will be located on the surface of the salient pole shoes. Okay, see, this is how the pole shoes looks like. Okay, now on the surface of the pole shoes, generally we will place the damper winding. Okay, so look at here, on the surface of the pole shoe, the damper windings are located. These are all the damper conductors located on the surface of pole shoe. Okay, this is a cross-sectional view only. If you look at the axial view, okay, this is how generally the pole shoes looks like. Axial, if I draw complete length, okay, this is how the pole shoes looks like, and then number of damper conductors are located like this. Okay, so these are the damper bars, and most important thing is all these damper bars are short circuited on both sides with the help of some conducting ring. Okay, we will use a conducting ring and we will short circuit all these damper bars. That means a damper winding will act like a closed circuit or open circuit. Yes, it acts like a closed circuit. Okay, it acts like a closed circuit. Even on this side also, the damper bars are short circuited. So similarly, like a squirrel cage rotor induction machine. In induction machine, there is a rotor named as a squirrel cage type. Even in those squirrel cage rotor also, number of copper bars will be distributed on the surface of the rotor, and all copper bars are short circuited on both sides using some end rings. Therefore, damper winding will act like a short circuited rotor distributed winding. That's all. Okay, we will use low resistance conductors to design damper winding. And what is the purpose of damper winding? It will reduce hunting process in synchronous machine. Okay, maybe it is generator or motor. How can hunting process can be reduced? To understand that, let me consider a simple example. Consider this is the stator part of the synchronous machine. Stator. Okay, this line is like a stationary line. The stator has three-phase distributed winding, that too carrying AC current. Whenever three-phase distributed winding is carrying AC current, it will create a stationary magnetic field or rotating magnetic field. I told you already, distributed winding carrying AC current will create rotating magnetic field. Therefore, this stator winding will create a rotating magnetic field at synchronous speed. So this is the position of stator magnetic field. Okay, now rotor will rotate at what speed? Ideally, under steady state condition, rotor will always be rotated at synchronous speed, right? So see, the rotor was rotating at synchronous speed. This is ideal case, steady state condition. All right, and this rotor will have distributed damper conductors. Okay, now one more thing, when the rotor was rotating, which torque will support the rotation and which torque will oppose the rotation? Remember guys, in case of generator, if I go back, yes, I told you generator means it will convert mechanical power to electrical power. Therefore, the input power is mechanical, and whatever the torque is created by this mechanical power, that will support the rotation of rotor. We call it as prime mover torque. And what is the output or load? This is a load power, right? Okay, and the load power is electrical power. Therefore, electromagnetic torque will oppose. Okay, always remember, supporting torque is from input side, opposing torque is from load side. As input is mechanical power from the prime mover, so prime mover torque will support the rotation, electromagnetic torque will oppose the rotation. This is in generator. What about in motor? In motor, input power is electrical, so therefore electrical torque will support the rotation. Load is mechanical power, so mechanical load torque will oppose the rotation. And remember, this is valid not only in synchronous machines, it is valid in DC machines as well as induction machines as well. Always remember, supporting torque will come from the input power side, opposing torque will come from the load side, because load will always oppose the rotation. And if I apply the same concept to synchronous generator now, okay, same concept to synchronous generator, right now it is a generator, therefore the supporting torque is prime mover torque. This is from mechanical power side. Opposition torque is from load side, that is electrical power side. Now under steady state, what will happen? Supporting torque and opposition torque both are equal. Okay, steady state. But let us create a disturbance. What happens if a sudden increase in load happened? Some disturbance. Okay, what happens if load suddenly increases? If load increases suddenly, load increases suddenly means opposition torque increases suddenly or supporting torque increases suddenly, opposition torque increases suddenly. So the moment when opposition torque increases, machine will experience acceleration or deceleration, deceleration. Therefore, what happens to rotor speed now? Decreases. Therefore, rotor will not rotate exactly at synchronous speed. It will now rotate at a speed less than synchronous speed. Now the rotor was rotating at less than synchronous speed. Imagine rotor reaches to this position, NR. Okay, prime mover torque is still supporting. Why rotor decelerated? Because opposition torque suddenly increases. Okay, therefore rotor decelerated. Now you see NR is equal to NS or less than NS, less than NS. The moment when NR becomes less than NS, a relative speed is created between stator field and rotor conductors, a relative speed, and that relative speed is nothing but NS minus NR. Okay, because of this relative speed, what happens? An EMF will be induced in damper winding. Remember, damper winding is on the surface of the rotor. Rotor is rotating at a speed less than synchronous value. That creates a relative speed between stator field and rotor conductors, and that relative speed is NS minus NR. And once EMF induces in damper winding, what will happen? Current circulates in damper winding. Why? Because damper winding is a closed circuit. And once current started to circulate, now damper conductors are normal conductors or current carrying conductors? Current carrying conductors. According to Lorentz force equation, whenever current carrying conductors are placed inside a magnetic field, they will experience a torque. Therefore, a torque is experienced by damper winding. We call it as damping torque. Now, according to Lenz's law, this damping torque will try to reduce this relative speed, because this is the cause and this is the effect. So the synchronous speed. If rotor reaches back to synchronous speed, then only I can say the relative speed reduces and damping, or you can say Lenz's law is satisfied. So this relative speed will create a new torque by damper winding, and that damper winding will push the rotor so that rotor will slowly reach the synchronous speed. Okay, remember, once a rotor reaches a synchronous speed, what happens to this relative speed? Zero, right? NR equal to NS. Once this relative speed is zero, damping torque becomes zero. The moment damping torque becomes 0, so far who is pushing the rotor? Damping torque. The moment when a damping torque becomes 0, rotor remains at ns only, or it will further accelerate? Yes, it will further accelerate because of inertia. We all know that rotating body will store some mechanical inertia. Because of that mechanical inertia, even though rotor reaches synchronous speed, even though this supporting damping torque becomes 0, rotor will not stop here. It will further accelerate because of inertia. Just like imagine you are pushing a car, okay, or any object. When you are pushing a car for certain distance and you suddenly leave that car, will that car stops there, or it will further move for some distance? Yet it will further move for some certain distance because of inertia. Similarly, even though rotor reaches synchronous speed, even though damping torque becomes 0, rotor will not stop here. It will further accelerate because of inertia. The moment when the rotor accelerated beyond synchronous speed, again the relative speed is created between what and what? Stator field and rotor conductors. And that relative speed will again create damper winding. Damper winding will try to reduce this relative speed. This time damper winding will oppose the rotation. Then only rotor will come back to synchronous speed. But rotor will not come to synchronous speed and stops here. It will come below synchronous speed because of inertia. And again above synchronous speed, again below, above. This is what? Swing, rotor swing. Okay. Rotor will oscillate around synchronous speed. Finally, after some time, the swings becomes 0 and the rotor will find a steady state exactly at synchronous speed. This is how damper winding will help to reduce the hunting phenomena in case of synchronous machine. Okay. Yes. Okay. Right. Now let us try to answer a question related to the hunting process. You see this question. This is a 1-mark question in GATE 2014 exam. Read the problem. In a synchronous machine, hunting is predominantly damped by what? Hunting. Yes, mechanical losses in the rotor, iron losses in the rotor, copper losses in the stator, copper losses in the rotor. The answer is copper losses in the rotor. Why copper losses? Because hunting is predominantly damped by damper winding only. Why damper winding was able to reduce hunting? Why? Because whenever load suddenly changes, rotor speed either decrease or increase based on the load change. That creates a relative speed between stator field and damper conductors, and that relative speed will induce an EMF in a damper winding. That EMF will create a current in a damper winding. That is what you need to understand. Okay, and this current will create the damping torque. Okay, at the same time, whenever current passes through damper winding, can I say it will create copper loss in the damper winding? Therefore, the hunting process is predominantly minimized by damping torque. Damping torque is due to current in the damper winding. The current in the damper winding will create some copper loss within damper winding or rotor, within the rotor. That is why copper losses in the rotor is the main reason for reducing the hunting process according to the given options. Okay. Yes. Now, let's see the next type of rotor. We have cylindrical rotor. Yes, as the name itself is indicating, cylindrical rotor means the shape of the rotor will be a circular shape. So see, this is the stator part. Okay, this is the stator. Now rotor will also be having the same circular shape. This is what we call it as cylindrical rotor. Now you tell me air gap is uniform or non-uniform? Yes, you take any position, the air gap is going to be uniform. If air gap is uniform, how can we create sinusoidal magnetic field? Yes, I told you in salient pole machine, the non-uniform air gap is the reason to make flux sinusoidal shape. Okay, but in cylindrical rotor machine, how can the flux becomes sinusoidal even though air gap is uniform? Yes, that is where distributed field winding will come into picture. Okay, we will use some slots in the rotor. Okay, these slots are used to place field winding. These are field winding conductors. Okay, therefore let's say this is 1, 1 dash, 2, 2 dash, 3, 3 dash, 4 4 dash. Now you see the field winding looks like concentrated field winding or distributed field winding. Yes, it looks like a distributed winding. Okay, so distributed field winding. Okay, so because of this distributed field winding, the field flux becomes almost like a sinusoidal wave. Why? Because what is the formula for flux? Flux is always equal to MMF divided by reluctance of air gap. Here, air gap reluctance is constant, whether it is a direct axis or quadrature axis. Why? Because air gap length is uniform. If you are confusing, I will erase these lines. The air gap length is uniform. That's why air gap reluctance is constant. If air gap reluctance is constant, then can I say field flux is only proportional to field MMF? So the shape of field flux will depend upon the shape of field MMF. Because I am using distributed field winding, the shape of MMF becomes almost like a sinusoidal. The field MMF with respect to space angle, if I take, it is almost like a sinusoidal shape, something like this. If the MMF is a sinusoidal, automatically the flux also sinusoidal. I said almost sinusoidal, but not exactly sinusoidal. You will learn in normal, regular class preparation, how can we get this sinusoidal shape. But in a quick review, you just need to understand flux becomes a sinusoidal shape because reluctance is non-uniform, or MMF is distributed because the MMF is distributed. Whereas in salient pole machine, flux becomes a sinusoidal because MMF is distributed or reluctance is non-uniform. Here, field winding is a concentrated winding. This is the field winding, guys. And you can understand it is a concentrated type winding. This cannot become sinusoidal MMF. MMF is like a flat line, okay? Because concentrated winding. Then the non-uniform air gap will help you to make flux sinusoidal. But in cylindrical rotor machine, reluctance is a constant value. Therefore, flux becomes a sinusoidal shape because the MMF is distributed. Okay, so it is going to be almost like a sinusoidal wave. This will be north pole and this will be south pole. Don't say, sir, it is a sinusoidal means it is alternating flux. It is not alternating. It is a time invariant flux only, but the shape is a sinusoidal, that's all. Okay, this is with respect to space, not with respect to time. Okay, yes. So obviously, as the air gap is uniform, centripetal forces effect is very, very less. Therefore, there is no mechanical damage to rotor even though you rotate the rotor at high speed. That means you can use this rotor for high speed prime mover applications. High speed applications, best example, steam turbine. Steam turbine means generally in thermal power stations and nuclear power stations. Okay, so high speed applications. Also, as you know, the speed is very high, we need less cross sectional area and more axial length. Less cross sectional area and more axial length for this particular machine. Okay, yes. Now the next question here is that where do we locate damper winding here? Just think about it. Where do we locate damper winding? In case of a salient pole machine, damper winding is located on the surface of the pole shoe, right? On the surface of the pole shoe. But here there is nothing called pole shoes in the machine. Okay. So where do we locate damper winding? Yes, the answer is damper winding is not required at all. In this machine, damper winding is not required. Why? Because the distributed field winding itself will act like damper winding. I repeat, the distributed field winding itself will act like damper winding. Okay, so in this rotor, the distributed field winding acts like damper winding. Acts like damper winding. Okay, so why don't we do the same thing in salient pole machine? Why we are specially using damper winding? Why? Because in salient pole machine, the field winding is a concentrated type. A concentrated winding cannot create torque during hunting process. That's why I need a special distributed winding known as damper winding. But in case of cylindrical rotor machine, already the field winding is distributed type. Therefore, you don't need additional damper winding to create damping torque during hunting process. So, the field winding itself will act like damper winding. Okay? Yes, that is important. That's all. These are the two types of rotors we have: salient pole rotor and cylindrical rotor. Salient pole rotor is used for low speed prime mover applications. Cylindrical rotor is used for high speed prime mover applications. Okay. So that's all about the construction of synchronous machine. Now let's move to the next important observation, that is about terminology of armature winding. Okay, so before moving to the EMF equation of a synchronous generator, first we need to understand what are the different terms that we will use in case of distributed armature winding. The first one is pole pitch. We can also call it as pole span. Okay, so it is the electrical angle between two adjacent north and south poles. Okay, let us consider this is the rotor part of a given machine. Let's say we have 4 poles in this machine. Let's say north pole, south pole, again a north pole, and we have a south pole. Okay. Now, what is meant by pole pitch? As I mentioned, it is the space angle between two adjacent north and south poles. You see here we have south pole, here we have an adjacent north pole. And this distance or this angle is what we call it as pole pitch. And if you look at this angle from your eyes, you can easily understand this is 90 degrees. Okay. But whatever angle we are able to observe physically with our eyes, that is what we call it as mechanical angle. So here the pole pitch in mechanical angle was equal to 90 degrees. But while writing mathematical equations, we must always use electrical angle only. Okay, so electrical angle is always equal to P by 2 times of mechanical angle. Right now, I am not doing the derivation. I hope you have idea about this particular relation. Okay, so even though you don't know, as a last quick review, you need not to learn the derivation part of it. Just remember this. Okay. But in regular studies, you have to understand what is the exact relation between electrical angle and mechanical angle through a derivation. Okay, anyway, electrical angle is always equal to P by 2 times of mechanical angle. And here how many poles are there? 4 poles are there. 4 by 2 into what is the mechanical angle between two poles? 90 degrees. Therefore, the electrical angle will become 180 degrees. And even if you take a 6 pole machine also, suppose if I take 6 poles, then what is the angle from one pole to another pole? 60 degrees. That is a mechanical angle. But when you convert into electrical angle, it will become 180 degrees. Therefore, pole pitch is always equal to 180 degrees electrical angle. Okay. Pole pitch is always equal to 180 degrees electrical. The mechanical angle may change from one machine to another machine, but electrical angle is always equal to 180 degrees. Correct? Okay, this is pole pitch. You can also give one more definition for pole pitch. It is the electrical angle consumed by each pole. Suppose if you take only this north pole, can I say this entire space belongs to this north pole only? And this is also called as pole pitch. Okay, and that will be equal to 180 degrees as well. Okay, right. So you can give two definitions. Either it is the angle between two adjacent north and south poles, or it is the angle consumed by one full pole. Understand? Okay. And pole pitch is always 180 degrees electrical degrees. All right. Now, the next important term we need to understand is what is mean by single layer winding and what is mean by double layer winding. A very simple difference. Let me divide the page into two parts. One side I will consider single layer winding. The other side I will consider double layer winding. Okay. So first of all, you need to understand that A coil will have at least how many sides? Two sides. Okay. You see, suppose if I wanted to draw a coil diagram, this is a one turn coil. Okay. So this is what we call it as one side of the coil, and this is the other side of the coil, one more side. Okay. Therefore, a coil will have two sides. One side will be generally under north pole, the other side will be under south pole. Even the coil may have any number of turns. Suppose you take a multi-turn coil. Suppose if you take a multi-turn coil like this, even in this coil also, this is one side and this is the other side. A coil will have two sides. Now, in single layer winding, what happens is, suppose if this is the core having some number of slots, and every slot is occupied by one coil side. Every slot, this is one coil side, second coil side, third coil side, fourth coil side. Okay. So this is not one coil, that circle represents one coil side. Okay. Suppose if the machine has, let us say, total 100 slots are available, just for example. If the machine has 100 slots, how many coil sides we can accommodate? 100 coil sides. Therefore, the number of coil sides are also equal to 100. 100 sides means how many coils? 50 coils. Therefore, number of coils are equal to 50. Okay, why? Because a coil will have two sides. 100 sides means 50 coils. Therefore, what is the relation between number of slots and number of coils? Yes, you can understand, number of slots are equal to 2 times of the coils. Okay, number of slots are equal to 2 times of the coils. Whereas on the other hand, double layer winding means, suppose if these are the number of slots we have. Okay, so every slot will be divided into two layers. One will be, obviously, this is the top layer and this is bottom layer. Virtually, the slot is divided into two layers. Now what we will do is that we will place one coil side on the top layer, the second coil side on the bottom layer. Again, one slot, one side on the top layer. That means every slot has how many sides? Two sides. Of course, the two sides doesn't belong to the same coil. This is one side of, let us say, coil number n. This is another side of next coil, n plus 1. Okay, like that. So every slot has two sides. One is on top layer, another one is on bottom layer. Suppose if you take the same example, assume the total number of slots are equal to 100. Then how many coil sides we can place? Number of coil sides are equal to 200, right? If a number of coil sides are equal to 200, then how many coils? Is it not 100 coils? Because every coil will have two sides. Therefore, what is the relation between slots and coils? That implies number of slots are equal to number of coils. Number of slots are equal to number of coils. Therefore, in a single layer winding, you need the number of slots double the number of coils. But in case of double layer winding, we need the number of slots equal to number of coils. Okay. Now, a question may arise here, which type of winding we will generally prefer? Yes, remember, always double layer winding is preferable. Okay. By default, double layer winding is always preferable, which is mechanically very strong compared to single layer winding. Okay. Yes. Next. Now, the next major important thing is coil pitch. We also call it as coil span. So very simple. Just like pole pitch, it is the angle between two adjacent poles. Coil pitch means it is the angle between two sides of a coil. I told you a coil will have two sides. Okay, this is one side of the coil, this is the other side of the coil. And the angle between, electrical angle between these two sides is what we call it as coil pitch. Coil pitch is the electrical angle between two sides of a coil, and that is represented with the letter beta. Okay, and based on this coil span value, coils are subdivided into two categories. First one, full pitch coils. Full pitch coils. Second one, short pitch coils. short pitch coils. Okay, so what is the difference between full pitch coil and short pitch coil? We will try to study now. Okay, yes, first let me consider full pitch coil. Okay, full pitch coil means the coil span will be equal to exactly one pole pitch. That's all. First of all, what is meant by pole pitch? We studied pole pitch means 180 degrees electrical. Therefore, if coil pitch is also equal to 180 degrees electrical, then we call it as a full pitch coil. Okay, so let's see what is meant by full pitch. Suppose we have a machine having north pole here and south pole here. This is the north pole position. This is the south pole position. Now what I am doing is I am placing one coil side, just a moment. Yes, I am placing one coil side exactly under north pole, the other coil side exactly under south pole. Okay, therefore you try to understand what is the coil pitch is equal to. Is it not equal to pole pitch 180 degrees electrical? Okay, so such type of coils we call it as full pitch coil. Now the advantage with full pitch coil is, suppose if this side has a voltage E at an angle 0, this side voltage will be exactly 180 degrees away. Okay, let us say this is conductor A, this is conductor B, or side A, side B. Now what is the total coil voltage VAB? Can I write VAB is nothing but VA minus VB, that is E at an angle 0 minus E at an angle 180. This will be equal to 2E. So it looks like algebraic summation E plus E, that is equal to 2E. That is a full pitch coil. But short pitch coil is different. What is short pitch coil? Short pitch coil means the coil pitch will not be equal to 180, it will be less than 180. Okay, that means you see, suppose this is north pole and this is south pole. So one conductor is exactly under north pole, one side is under north pole, but the other side is not exactly under south pole, it was shorted by some angle. Okay, so tell me here, what is this angle? That is full pitch, 180 degrees. But now the coil pitch is not 180, it is less than 180. The beta value was less than 180. That means, can I say there was some short pitch angle here? Yes, this is what we call it as short pitch angle alpha. Very important. This alpha is known as short pitch angle alpha. So short pitch angle means it is the small angle by which the coil was shorted from full pitch. And if you write the relation between alpha and beta, can I write beta plus alpha together is equal to 180 degrees? So alpha plus beta is equal to 180 degrees. From this, the short pitch angle alpha is equal to 180 degrees minus beta, or the pitch coil span beta is equal to 180 degrees minus alpha. Anything is valid. Okay. So what is this alpha? Alpha is the short pitch angle. Therefore, you see now, suppose if this side the voltage is, let us say, E at an angle 0, then the other side, can I say the voltage is E at an angle 180 degrees minus alpha. It was shorted by some angle alpha. Therefore, let us say this side is A, this side is B, then what is the voltage? VAB is equal to A side E at an angle 0, but B side E at an angle 180 degrees minus alpha. So if you add both of them vectorially, you will get the answer 2E cos alpha by 2. This is not like algebraic summation, this is like vectorial summation. And this factor cos alpha by 2 is what we call it as a short pitch factor, okay, or simply pitch factor. Okay, let's see the next important term, pitch factor. Pitch factor represented with the letter Kp. Okay, right, pitch factor. So what is the definition for pitch factor? Pitch factor is defined as the ratio between short pitch coil voltage to full pitch coil voltage. It is the ratio between short pitch coil voltage to full pitch coil voltage. full pitch coil voltage. Yes, what is the short pitch coil voltage? Just now we studied, it is 2E cos alpha by 2. 2E cos alpha by 2. What is the full pitch coil voltage? That is directly 2E, right? 2E. Therefore, 2E will cancel. That means the pitch factor is equal to cos alpha by 2. And remember, for short pitch coils, this is always less than 1. Because we know cos of any angle is always less than 1. What if alpha is 0? Then pitch factor will be equal to 1. So strictly speaking, I must write pitch factor is either less than or equal to 1. If alpha is 0, what is meant by alpha is 0? There is no short pitch angle. If this short pitch angle is 0, indirectly if I use a full pitch coils, then alpha will be 0, then pitch factor will be exactly equal to 1. But in case if I use a short pitch coil, then alpha will not be 0, it will be a finite value, then pitch factor will be less than 1. Rather than equal to 1, it will be less than 1. Okay, so that is pitch factor. Now we will try to understand what are the advantages and disadvantages of short pitch coil. See, advantage of short pitch coils. Okay, we have to prove everything. In normal class we use it to prove every point, but here we are revising every point. What is the advantage? First advantage is harmonic voltages can be neutralized. Harmonic voltages can be neutralized. How can we neutralize harmonic voltage? Very simple, pitch factor selection, the short pitch angle selection. What is the short pitch angle required to neutralize fifth harmonic voltage? Yes, to neutralize fifth harmonic voltage, the short pitch angle required is alpha is equal to 180 degrees by 5 electrical angle. If you use this much short pitch angle, then fifth harmonic voltage can be neutralized. Similarly, what is the short pitch angle to neutralize nth harmonic voltage? To neutralize nth harmonic voltage, the short pitch angle required is equal to 180 degrees by n electrical degrees. That's all. By using a suitable short pitch angle, we can neutralize harmonic voltages. And what is the formula for pitch factor with respect to harmonic voltages? Yes, Kp is equal to cos n alpha by 2. See, remember, cos alpha by 2, this is the pitch factor for fundamental harmonic. This is with respect to fundamental harmonic. Suppose if I select nth harmonic, then the pitch factor will be equal to cos n alpha by 2, where n is nth harmonic. If it is a 7th harmonic, then it is cos 7 alpha by 2. 9th harmonic cos 9 alpha by 2. 11th harmonic cos 11 alpha by 2. For nth harmonic, it is cos n alpha by 2. And to neutralize the nth harmonic voltage, what is the short pitch angle required? I should write alpha right here. Yes, this is alpha. The value of alpha is equal to 180 degrees by n electrical degrees. If I use that much short pitch angle, harmonic voltages can be neutralized. Okay. Also, the disadvantage. What is the disadvantage of short pitch coils? Yes, the disadvantage is resultant voltage is less than full pitch coil. Okay. The final voltage or final EMF is less than full pitch coil. Less than full pitch coil. In full pitch coil, what is the resultant voltage? That is 2E. That is algebraic summation. Suppose if this is a 10, this is a 10, 10 plus 10 is equal to 20. But in short pitch coil, it is not 2E. 2E multiplied by one factor, this factor is less than 1, right? Suppose if this is a 10 and this is a 10, resultant answer will be 20 or less than 20, less than 20. Therefore, when I use a short pitch coils, output voltage will be less compared to full pitch coils. Okay, but even though output voltage is less, we are still using short pitch coils because the advantage is harmonic voltages can be neutralized. What is the advantage if harmonic voltage is neutralized? Output voltage becomes more sinusoidal. Okay, that is why short pitch coils are preferable in case of synchronous generator as well as induction machine as well. Even in induction machine also, to neutralize harmonic voltages, we will use short pitch coils. All right. Okay. Now, the next important term is slot angle, also known as slot pitch. As the name itself is indicating, it is the angle between two adjacent slots, or it is the angle occupied by each slot. Let's take a small example. Consider this is the machine that I have. Suppose this machine has a number of slots. Okay, so like this. Now if I ask you the question, what is the angle from first slot to second slot? What is this angle? Second slot to third slot, what is the angle? That is what we call it as slot angle or slot pitch. Okay, and slot pitch angle gamma is equal to 180 degrees divided by slots per pole. Electrical angle. Remember, anything that we are expressing mathematically, it must be electrical angle only. 180 degrees divided by S by P, where S by P is known as slots per pole. Slots per pole. So if you know how many slots are there per each pole, then you can easily find out the slot angle, 180 degrees by slots per pole. Okay, yes. This is the next most important term in armature winding. Next, slots per pole per phase, a very important term represented with the letter M. Number of slots per pole per phase. How many number of slots are there per each pole under each phase? That is slots per pole per phase. Okay, this factor is very important to determine distribution factor of armature winding. And based on the value of M, again armature windings are subdivided into two categories known as fractional slot pitch winding and integral slot pitch winding. Let me take a simple example. Suppose I have a machine with, let us say, 48 slots are there, number of poles are 4 and number of phases are 3. 3-phase machine, total 48 slots are there with 4 poles. Can you calculate what is the value of M? M is number of slots per pole per phase. And how many slots are there? Obviously 48 divided by 4 poles with 3 phases. Okay, so therefore the value of M is equal to 4, exactly 4. Let me take one more example. Consider we have a machine. Let us say total number of slots are equal to 54. Number of poles are 4 and it is a 3-phase machine. Okay, 3-phase machine. Calculate the value of M here also. M is always equal to number of slots per pole per phase. Yes, there are 54 slots available per 4 poles and 3 phases. Okay, 54 by 12, is it not 4.5 exactly? Therefore, if you look at both M values, in the first example, M is an integer or it is a fractional number? It is an integer number. As M is an integer, we call it as integral slot pitch winding. Okay, such type of winding is known as integral slot pitch winding. Integral slot pitch winding. Whereas on the other hand, if you look at the second example, what is the M value? 4.5, which is an integer number or fractional number? Yes, it is a fraction, so we call it as fractional slot pitch winding. That is fractional slot pitch winding. And which type of, that means whether it is integral slot pitch or fractional slot pitch, we will decide based on the value of M. Okay, if M is an integer, integral slot pitch winding. If M is a fraction, fractional slot pitch winding. And which winding we will generally use? Yes, we always use fractional slot pitch winding. This is preferable because by using a fractional slot pitch winding, slot harmonics can be slot harmonics can be neutralized. Slot harmonics can be neutralized by using fractional slot pitch winding. That's why in practical synchronous machines, we will always use fractional slot pitch winding. Okay, right. Now, the next important term is phase spread. Okay, represented with the letter sigma. What is meant by phase spread? Very simple. It is the electrical angle occupied by each phase winding under each pole. Okay, let me tell you. Imagine this is the stator part of the machine. And assume that our machine has 4 poles. Okay, I said 4 poles. That's why I divided the machine into 4 parts. Let's say this is North Pole region, South Pole region, North Pole and South Pole. There are 4 poles. And every pole region I need to divide into 3 parts because the machine is a 3-phase machine. Let's consider 3-phase winding. If I consider 3-phase winding, let us divide every pole into 3 equal parts. Okay, like this. Let us say this is phase A part, B part and C part. Now, what is meant by phase spread? It is the angle occupied by, let me make it more clear. Yes, phase spread means it is the angle occupied by each phase winding under each pole. If you take one pole only, one pole means what is the angle, guys? 180 degrees electrical. Physically it looks like 90, but electrically it is 180. This is overall 180. And that 180 degrees is divided into 3 parts. Then what is the angle occupied by each phase winding? Is it not 60 degrees? 180 degrees by 3. That is what we call it as phase spread. This is phase spread. This area. That is the area occupied by which winding? Phase A winding under one pole only, one pole. Therefore, phase spread is, it is the angle occupied by each phase winding under each pole. Therefore, for 3-phase winding, what is the phase spread? The sigma is equal to 60 degrees electrical. Suppose what if the machine has a 2-phase winding? If it is a 2-phase winding, I have to divide this 180 degrees into 2 parts. Then each winding will consume 90 degrees. Therefore, for 2-phase winding, the phase spread is equal to 90 degrees. What if the machine is a single-phase machine? Then the entire pole will be occupied by only one phase winding. Therefore, for single-phase winding, the phase spread will be equal to 180 degrees electrical. Okay, so for 3-phase winding 60 degrees, 2-phase winding 90 degrees, single phase winding 180 degrees. Okay, and there is a relation between phase spread, slots per pole per phase and slot angle. The relation is phase spread sigma is equal to m gamma. Sigma is phase spread, m is slots per pole per phase, gamma is the slot angle or slot pitch. So sigma is equal to m gamma. This is a relation you need to remember. I am not proving these equations, you know, there will be derivations behind them. Understand? So sigma is equal to m gamma. Okay. Now, the last term in armature distributed winding is distribution factor. We can also call it as breadth factor as well. Okay, distribution factor. What is the distribution factor? Very simple. It is the ratio between distributed winding voltage to concentrated winding voltage. Concentrated winding voltage. So what is the difference between distributed winding and concentrated winding? You take one example. Suppose you take transformer as an example. Consider this is a magnetic core in transformer, and I am wounding a wire with, let us say, 4 coils, 4 turns. Let us say first turn has a voltage 10 volt, second turn also has a 10 volt, third turn 10 volt, fourth turn also 10 volt. Now if I ask you what is the total voltage across this winding, then what is your answer? Is it not 40 volt? Why? Because each turn has 10 volt and you are just adding all the 10 volts together algebraically and you will get resultant voltage 40 volt. This is concentrated winding. And there is no phase angle difference from first turn to second turn. All turns are in phase with each other, same flux will link them. Therefore, all these voltages are at the same phase angle. Algebraic addition is possible. That's why 40 volt is coming. On the other hand, let us say we have a distributed winding where conductors are placed in number of slots like this. Let us say I have one conductor in first slot, okay, second conductor here, third conductor here, fourth conductor here. All conductors are having 10 volt only. Now what is the resultant voltage of all these four conductors together? It is not 40, it is less than 40. Because you can't add the voltages algebraically. Why? Because from first slot to second slot there is a phase angle difference. We call it as gamma. Second slot to third slot, again phase angle difference is there. Third slot to fourth slot, again phase angle difference is there. Therefore, there is a phase angle difference. So you can't add all voltages algebraically. We have to add vectorially. So in this case, the resultant voltage is 10 at an angle 0, first slot, 10 at an angle gamma, second slot, 10 at an angle 2 gamma, third slot, 10 at an angle 3 gamma, fourth slot. Like that, the order will continue. And we all know vectorial addition is always less than algebraic addition. This is what distributed winding is. Now, which is easy to calculate? Can I say the easy calculation is always concentrated winding voltage, which is just algebraic summation. But practically in our synchronous generator, we are using concentrated winding for armature or distributed winding. So, if you know concentrated winding voltage, how to calculate distributed winding voltage? Just to cross multiply. If I cross multiply, can I say voltage of distributed winding is simply equal to exactly KD times of concentrated winding voltage. Okay, and concentrated winding voltage is easy to calculate, and that easy calculation multiplied by KD will give you distributed winding voltage directly. So that is why KD calculation is very important. Distribution factor. Yes, what is the formula for a distribution factor? Yes, distribution factor is equal to sine m gamma divided by 2 by m sine gamma by 2. This is the direct formula. There will be derivation behind this. I am not doing that. So distribution factor is equal to sine m gamma by 2 divided by m sine gamma by 2. We know what is m here. Slots per pole per phase. Gamma is slot angle. Suppose if gamma is very small, we can write an approximate formula. We know when angle is very small, sine of that angle is almost equal to that angle, right? If theta is very small, sine theta can be written as theta. In that case, the approximate formula for a distribution factor is sine m gamma by 2 divided by the denominator already m is there. And if gamma is very small, sine gamma by 2 is approximately equal to gamma by 2. And to convert into radians, we will multiply with pi and divide with 180. This is the approximate formula for a distribution factor, and this is the exact formula for a distribution factor. Okay? And in that approximate formula again, what is m gamma? I told you already. M gamma is nothing but phase spread. And we know phase spread is a fixed value for 3-phase, 2-phase and a single phase. Therefore, I can substitute these angles directly in this approximate formula so that I can calculate a distribution factor directly. Yes, the distribution factor for 3-phase winding will be equal to 3 by pi directly. If you substitute that m gamma is equal to 60 degrees in this formula, sine 60 by 2 divided by 60 by 2 into pi by 180, you will get 3 by pi. And if you do the same thing for a 2-phase machine, m gamma is equal to 90 degrees, then it will become 2 root 2 by pi. That is the distribution factor for 2-phase machine. What if it is a single phase machine? The distribution factor for single phase machine will become 2 by pi. These are the approximate distribution factors. You can directly use them, especially when the question is multiple choice type. You can choose these approximate distribution factor and you can choose the nearest answer. But if the question is a numerical answer type, you have to use the original formula, original distribution factor formula and calculate the accurate value of distribution factor. Okay. However, the error will be very small whether you use approximate value or accurate value. So, especially when the question is a multiple choice type, you can directly use these distribution factors. Okay. Now, once we know distribution factor and pitch factor, we can write down winding factor formula now. Winding factor represented with the letter Kw. So Kw is equal to pitch factor multiplied by distribution factor. If you multiply both of them together, then you will get winding factor information. Okay. So this is the terminology about armature winding. Understand? Now let us talk about EMF equation of alternator. So we have seen the terminology of armature winding so far, and we have observed what is meant by pitch factor, what is meant by distribution factor, etc. Okay. So now let us see the EMF equation of alternator. As I told you, the alternator will have two windings. One is field winding, another one is armature winding. So we know the field winding, just a moment. Okay, so we know the field winding is excited using a DC supply. So imagine this is the field winding that we have. Okay, so we are exciting this field winding with a DC supply. We call it as a field voltage and the current is known as a field current. Now this field current will develop a flux in the air gap of the machine known as field flux. Now that field flux will cross the air gap and link armature winding of the alternator. Alright, so an EMF will be induced in the armature winding due to field flux. Okay, that is what we call it as field induced EMF. Okay, so we call it as field induced EMF. See, this is the EMF induced in armature winding due to field flux. That's why the name is field induced EMF. Field induced EMF doesn't mean it is the voltage in field winding. It is the voltage in armature winding due to field flux. That's why we call it as field induced EMF. Okay. In some textbooks, this is also written as generated induced EMF. Anything is same. And one more thing, all of you have to remember that even though our machine is a three-phase distributed armature winding machine, the EMF equation is always developed per phase only. The EMF equation is always developed per phase. So whatever the equation I am going to write right now, that is per phase induced EMF of the alternator. Okay, and it will be equal to 4.44. I am not doing the derivation. Okay, so directly I am writing the equation 4.44 into field flux per pole into frequency into number of turns per phase multiplied by winding factor. Okay, and remember this is the voltage induced per each phase, and we need to understand what each term is representing here. Okay, so remember the phi f value here is representing field flux per pole. Field flux per pole. Okay, and f is representing the frequency of induced EMF. Okay, so earlier we discussed about frequency of induced EMF. F is equal to P into N by 120, and T represents number of turns per phase. Number of turns in armature winding per phase. So total number of turns are not important. Number of turns per phase are important. And Kw is winding factor. We know Kw is equal to pitch factor multiplied by distribution factor. So we also call it as winding factor of the machine. Winding factor. Understand? So if you use this equation, you will be able to get the generated EMF of the alternator. So remember, phi f is nothing but field flux per pole. And this field flux magnitude will depend upon the field current magnitude. Understand? And frequency will depend upon the speed at which the machine was rotating. And number of turns in armature winding per phase, number of turns, not number of coils or number of conductors, number of turns per phase. And Kw is pitch factor multiplied by distribution factor. What is the formula for pitch factor? If I write, we already discussed, pitch factor is equal to cos alpha by 2, where alpha is the short pitch angle. Distribution factor is equal to sin m gamma divided by 2 divided by m sin gamma by 2. That is the value of distribution factor. And remember, whatever the equation I have written here, this is the induced EMF per phase in armature winding with respect to fundamental component. This is by default, it is fundamental harmonic EMF. Sometimes in the numerical questions, the examiner may also ask you to determine what is the third harmonic induced EMF or fifth harmonic induced EMF. Yes, which values will change from fundamental harmonic to third harmonic to fifth harmonic, which values will change? The flux per pole value will change. For every harmonic, flux per pole will not be equal. Okay, suppose if fundamental flux per pole is, let us say, 10 milliweber, third harmonic flux per pole magnitude will decrease. It may be 2 milliweber or 3 milliweber only. If you go to fifth harmonic, the flux per pole will further decrease. Okay, that will be mentioned in the problem always. Okay, yes, flux per pole will change. Next, frequency will change. We all know if a fundamental component frequency is F, third harmonic frequency will be 3 into F. Fifth harmonic frequency will be 5 into F. Seventh harmonic frequency 7 into F. Therefore, with respect to harmonic, the frequency value will change. Next, number of turns doesn't change because it's a physical term, right? Once a construction is completed, the number of turns per phase will not change. Next, winding factor will change. Yes. Why? Because what is the formula for winding factor? Kp into Kd. Coming to Kp, this is fundamental harmonic Kp. What if I ask you to write down third harmonic pitch factor? We know third harmonic pitch factor will be cos 3 alpha by 2. Fifth harmonic pitch factor cos 5 alpha by 2. Like that, whenever harmonic component changes, pitch factor value will change. At the same time, distribution factor will also change. If I ask you to write down what is a third harmonic distribution factor, yes, it will become sin m doesn't change, but these angles will change. If gamma is fundamental harmonic slot angle, then for third harmonic 3 gamma, gamma becomes 3 gamma divided by m sin 3 gamma by 2. Okay, if you wanted to write down distribution factor for fifth harmonic, sin m into, okay, fifth harmonic, sin m into 5 gamma by 2 divided by m sin 5 gamma by 2. So, whenever harmonic component number changes, the pitch factor and the distribution factor also changes, thereby the winding factor will also change. Okay, so this number of turns remains a constant value. Okay, so using that, you can find out harmonic voltages also based on the given information in the problem. But if there is no information, by default, you are calculating fundamental harmonic EMF only. Understand? So this is the induced EMF per phase in an alternator. Understand? Okay. Now, our next discussion is armature reaction in case of synchronous generator as well as a synchronous motor. Now, so far we discussed the basics of a synchronous machine, okay, how synchronous machine will work, what are the fundamentals of synchronous machine. From here onwards, every concept I will try to discuss for both generator as well as motor. Okay, so first of all, let us understand what is meant by armature reaction. As we discussed so far, there are two windings in synchronous machine. Okay, one is field winding. Okay, another one is armature winding. Another one is armature winding. Now we know we are exciting field winding with DC current known as field current. Whenever you excite any winding with some current, automatically MMF will be created because MMF is number of turns into current. So therefore, this field current will create an MMF known as field MMF. Now, because of this MMF, a flux will be generated in the machine. We call it as a field flux. Okay. Similarly, there is one more winding in the machine known as armature winding. Coming to armature winding, we are going to excite armature winding or it will generate the current. Yes, so suppose if the machine is a generator, you come back to this circuit diagram. Okay, this is a generator, guys. The field winding we are exciting with what? DC supply. Therefore, it will create a flux known as a field flux. Okay, it will create a flux known as a field flux. That field flux will cross air gap and link armature winding. This is armature winding. So, an EMF will be induced in armature winding. Okay, for just for moment, let me erase these things. So, an EMF is induced in armature winding. We call that EMF as generated EMF or field induced EMF. Okay. Now, once EMF is induced, immediately current will be generated or cannot be generated. The moment when EMF is induced, you look at this, it looks like open circuit. That means I have not connected any load here. If you don't connect any load, even though voltage is generated, current will not be generated, right? Because it is open circuit. So the machine will be able to generate the current only when the load is connected. So imagine a load is connected to this generator. So the moment when the load is connected, immediately this armature winding will generate a current. We call it as armature current. So armature winding will generate a current only when load is connected to the generator. I'm keeping generator in mind. Okay. So armature winding will generate a current known as armature current once load is connected. Therefore, can I say armature winding is now also carrying some current through it? So whenever current is passing through armature winding, an MMF will be created within armature winding. We call it as armature MMF. And that armature MMF will create a flux known as armature flux. Therefore, you can understand there are two magnetic fields in the synchronous machine. Now the point is the effect of this armature MMF or armature flux on main field flux is what we call it as armature reaction. So armature reaction is defined as the effect of armature flux on main field flux. We can also discuss armature MMF as it is the effect of armature MMF on main field MMF. This is another definition. So armature reaction is defined as the effect of armature flux on main field flux or the effect of armature MMF on main field MMF. Anything can be treated as armature reaction. Now let us understand the armature reaction effect in both generator as well as in motor with respect to the power factor. Okay. All right. So first I will consider a synchronous generator, that too operating with lagging power factor load. Imagine the load is a lagging power factor type. So to understand the effect of armature reaction, I have to draw phasor diagram of the machine. Okay. So to draw phasor diagram, we will always take main field flux as reference. I am taking main field flux as reference. Now this main field flux will cross air gap and induces an EMF in the armature winding. We call it as field induced EMF. Now remember, according to Faraday's law, the induced EMF will always lag the field flux by 90 degrees. The induced EMF will lag the field flux by 90 degrees. This is according to Faraday's law. I am not inventing anything new here. So according to Faraday's law, induced EMF will always lag the corresponding flux by 90 degrees. Okay, we can prove it by drawing a waveform, but I'm not going through the proofs right now. Okay, so if I apply that concept, this is the field flux. Therefore, the field induced EMF will lag this flux by 90 degrees. How do you draw lagging phasor? Yes, I hope you know that. In case if anybody don't know, please understand any phasor rotating in clockwise direction, that is a lagging phasor. any phasor rotating in anti-clockwise direction, that is considered as a leading phasor. Okay, basic circuit knowledge. So clockwise rotation is a lagging phasor, anti-clockwise rotation is a leading phasor. Okay, now keeping that point in mind, I can draw induced EMF now that will lag this field flux by 90 degrees. Therefore, here we will get field induced EMF. Okay, now this is lagging. Induced EMF will lag the flux by 90 degrees. Now this induced EMF will generate a current. And what is the type of the current? Yes, I am considering a lagging power factor load. Therefore, the current will lag the voltage by some finite angle. This is the armature current. Why armature current is lagging the voltage? Because the load is a lagging power factor load. Okay, so this is what we call it as power factor angle, represented with the letter psi. Remember, this psi is what we call it as internal power factor angle. We will learn soon what is internal power factor angle, etc. Now, if this is armature current phasor, can I say now this armature current will generate a flux in the machine known as armature flux? And where will be armature flux? Yes, we know flux and current are always in phase. Therefore, armature flux is also in the same phase. That is armature flux. Now, I can resolve this armature flux into two components. Yes, this is one component and this is another component. Okay, if I add this first component and second component together, then I will get the resultant armature flux. And if you look at this component right now, which is the horizontal one, it is in the direction of main field flux or exactly opposite. That is what we call it as demagnetizing armature flux component. And you look at this vertical component which is perpendicular to main field flux. The component which is perpendicular to main field flux, we call it as cross magnetizing armature flux component. Therefore, when a synchronous generator is feeding a finite lagging power factor load, it creates two types of armature flux components. One is completely demagnetizing main field flux. Another one is completely cross magnetizing main field flux. Therefore, I can say the armature flux has partial demagnetization and partial cross magnetization. And what if you apply the same concept to synchronous motor? I told you the only difference between generator and motor is direction of current. If it is a synchronous motor, armature current will be generated by the machine or taken by the machine. So armature current direction reverses. If armature current direction reverses, armature flux direction will also reverse. If armature flux direction reverses, demagnetization component becomes magnetization component. This cross magnetization component will again become cross magnetization only. Even though it is opposite direction, it is still perpendicular cross magnetization. Okay, so exactly opposite in generator and motor. So keeping all these points in mind, let me write a tabular column where we can understand the effect of armature, reaction for all the types of, power factors. Okay, see this. So I am considering the power factor in the first column and synchronous generator in the second column and synchronous motor in the third column. Okay, all right. So there are different types of power factors I am going to consider. So first one is zero power factor lagging. That means complete lagging. Cos 90 degrees is what zero power factor means. Okay. Next, zero power factor leading. Next, purely unity power factor. Next, finite lagging power factor. That is not 90 degrees lagging, some 30 degrees or 40 degrees lagging current. Next, finite leading power factor as well. Finite leading power factor also. Yes, what is the first observation? When the power factor is zero power factor lagging, that means current lagging the voltage by 90 degrees. Suppose if armature current lagging the voltage by 90 degrees, you will get armature current here. Then armature flux is also in the same phase. That means armature flux is completely demagnetizing. Okay, so in generator, the armature reaction will become pure demagnetization. If it is a pure demagnetization in generator, what is the effect in motor? Pure magnetization. Therefore, the motor effect will be pure magnetization. Now, if you apply the same concept to zero power factor leading type, yes, in a generator it will become pure magnetization. In motor, it will become pure demagnetization. Actually, for every individual power factor, you need to draw this phasor diagram so that you will get the answers easily. But we are not drawing all the phasor diagrams. One example phasor diagram I have drawn so that I hope you can implement the same concept to each and every power factor. Now, if you consider unity power factor, okay, unity power factor means current will be in phase with voltage. See, voltage is here, then armature current is also in the same phase because unity power factor. Then armature flux is also in the same phase. That means armature flux is completely cross magnetizing. Okay, so that is what? Pure cross magnetization. Pure cross magnetization. Even in motor also, even if you reverse the current, you will get still cross magnetization only. Pure cross magnetization. Okay, now let us understand or let us apply the same concept for finite lagging power factor. Finite lagging means that is what we studied. Current is not lagging by 90 degrees, it is lagging by some finite angle called as psi degrees. Then armature reaction is partial demagnetization, okay, and partial cross magnetization. Okay, if you apply the same concept to motor, exactly opposite. Demagnetization becomes magnetization. So it becomes partial magnetization and partial cross magnetization. Okay, so what if you apply the same concept to finite leading power factor? So demagnetization becomes magnetization. So partial magnetization and partial cross magnetization. Cross magnetization. Okay, coming to synchronous motor, it will become partial demagnetization and partial cross magnetization. Okay, so this is about the effect of armature reaction in case of synchronous generator and synchronous motor. Okay, so I request, it is not possible to by heart everything. You need to draw the phasor diagram to develop the armature reaction in both motor as well as generator. But the good thing is, if you remember generator concepts, motor concepts are exactly opposite. Demagnetization becomes magnetization because I told you that the only difference is current direction reverses. Okay, so I'll give you, yes, take 1 minute time. Okay, I'll give you half minute, 30 seconds exactly. Draw the phasor diagram for finite leading power factor or ZPF leading power factor. Okay, ZPF leading power factor in synchronous generator. Okay, draw the phasor diagram, understand what is the nature of armature reaction. Come on, 30 seconds time for you, or else you just follow my instructions. Yes, if you have any rough paper with you, just open that rough paper, take a pen and try to do the analysis. First take main field flux as reference. Okay, take main field flux as reference. Okay, then induced EMF is always lagging the flux by 90 degrees, right? Induced EMF is always lagging the flux by 90 degrees. Okay, now that induced EMF will generate a current which is at a power factor of 0 leading. What is mean by power factor? Cos phi, right? Cos phi is equal to 0 degree. 0 means indirectly power factor angle is 90 degrees. Okay, so if you take main field flux as reference, induced EMF is lagging the flux by 90 degrees. Lagging means anti-clockwise direction. Now this EMF will generate a current which is 90 degrees leading. I said leading power factor. So this is the voltage. Keep your pen on voltage. Rotate your pen in anti-clockwise direction by 90 degrees. Therefore, armature current will come at this particular time. So this is armature current. If this is armature current, can I say armature flux will also be in the same phase? Now you can understand what is the angle between main field flux and armature flux. Can I say both are in phase with each other? Main field flux and armature flux both are in phase. That means, can I say both are magnetizing each other? Yes. Armature flux and main field flux both are magnetizing each other. So that is what? For ZPF leading power factor, in case of a generator, the magnetization is pure magnetization. The effect of armature reaction is pure magnetization. And if it is magnetization in generator, in motor will become demagnetization. Understand? Okay. So what is this magnetization and demagnetization? Very simple. When I say armature flux is magnetizing main field flux, that means both fluxes are adding. That means resultant flux will increase. When resultant flux increases, can I say resultant voltage will also increase? So that leads to rise in voltage of the generator. When I say demagnetization, armature flux will be demagnetizing the main field flux. That means resultant flux will decrease. If resultant flux decreases, resultant voltage will also decrease. That means drop in voltage effect. Okay, so this magnetization, demagnetization represents the change in the resultant voltage, which may be either rise in voltage or drop in voltage. It depends upon the load power factor. Okay, yes. Now, you see there was a question in GATE 2006 exam. It's a 1 mark question. A synchronous generator is feeding a 0 power factor lagging load at rated current. What is the effect of armature reaction? See, synchronous generator. The question is from a generator feeding 0 power factor lagging. 0 power factor lagging means, can I say ZPF lagging power factor? Just a moment. Okay, ZPF lagging power factor. ZPF lagging power factor means what is the effect of armature reaction? We have just studied generator ZPF lagging power factor. That means it is pure demagnetization. So the answer is demagnetization, option B. Suppose if it is ZPF leading power factor, it would have been magnetization. If it is unity power factor, cross magnetization. See, very simple question. It was given for 1 mark. Okay, right. All right. Now we are entering into numerical aspects of synchronous machine. So far we discussed all theoretical concepts. So now the first concept is, yes, I must say this is module number 2, okay, in a synchronous machine, after the basic working principles. Equivalent circuit of synchronous generator. We have to develop the equivalent circuit in a step-by-step manner, but I am directly drawing here. Yes, to develop the equivalent circuit of a synchronous generator, we have to consider 3 important effects. First one is armature reaction effect. Okay, so this is armature reaction effect. I will show it here. Yes, this is effect of armature reaction. And then the second effect is leakage flux effect. Okay, effect of leakage flux. Okay, leakage flux effect. And finally, armature winding resistance effect. Armature winding resistance effect. And we just studied what is the effect of armature reaction already. It may be either demagnetizing or magnetizing. Okay, anything it may be. Demagnetization means it represents a drop in voltage. Magnetization means it represents a rise in voltage, and that is shown using an inductive reactance in series with the circuit. And that reactance is what we call it as armature reactance of the machine. Armature reactance. And the voltage across this reactance, it may be either a drop in voltage or rise in voltage, it depends upon the load power factor. Okay. Yes. So the effect of armature reaction is represented using an inductive reactance known as armature reactance. Now the next effect is leakage flux effect. We all know what is meant by leakage. It is the flux leaking out of the machine. That means it is a flux we are losing or flux we are gaining. Yes, the flux the machine is losing. That lost flux will definitely represents drop in voltage. Okay, so therefore any power factor, the load may be lagging power factor or the load may be leading power factor, whatever the power factor, leakage will always represents drop in voltage only, drop, because it is a flux we are losing from the machine. Okay, so the expectation is 100% flux will link stator and rotor, but reality is 95 to 96% flux will link both stator and rotor, 3 to 4% flux will leak. Okay, that represents a drop in voltage. Next, winding resistance. This is a minor effect that will also represent a drop in voltage. Whenever current is passing through any winding, every winding will have some finite resistance, and resistance will have two disadvantages. One is voltage drop across the resistance. Second one is copper losses. Therefore, whether load is lagging power factor type or leading power factor type, resistance will always represent a drop in voltage only. Okay, so the only effect which may be drop or may be rise, it is armature reaction effect that depends upon load power factor. Okay, so now can we simplify the circuit here? Yes, there are two reactances, inductive reactances are there. I can combine both of them and I can together represent as a single reactance. That is what we call it as synchronous reactance. Same circuit diagram. This is a field circuit, this is armature circuit, and I just added both reactances together. So we got a single reactance known as synchronous reactance. That is XCS, synchronous reactance. Can I say synchronous reactance is a combination of armature reactance and leakage reactance together, combination. Okay. And then we have resistance also, RA. Now can I combine this resistance plus reactance as an impedance? Yes, we call it as synchronous impedance, ZS, synchronous impedance. Okay, ZS. Everything is in ohm. Okay. And also you can observe from the circuit diagram, there are two voltages involved in the equivalent circuit. Okay. One is induced EMF, another one is terminal voltage. And always the rule is, or always the fact is, induced EMF will lead the terminal voltage by an angle known as delta. That delta is called as load angle or power angle. Load angle or power angle. We will prove it using a phasor diagram also. Okay. And remember, armature current will flow from induced EMF to terminal voltage. Okay, this is the circuit diagram of synchronous generator. So VT is the terminal voltage, that is the final output voltage of the machine. EF is induced EMF of the machine. Understand? Okay. So this is the equivalent circuit, and very important one to develop the phasor diagrams. Okay, any kind of mathematical equations. Okay. Now let us try to develop the equivalent circuit of synchronous motor in a similar manner. As I told you, what is the only difference? Field circuit will not have any difference. Motor or generator, in both machines, the field winding is excited with DC supply. But the difference will come in armature circuit. Now machine will generate the current or absorb the current. Yes, the motor will absorb the current from a source. Okay. Let us draw the equivalent circuit of synchronous motor. Okay. So the field circuit is as usual. This is the field winding excited using a DC supply. This is a field voltage. This is a field current. Coming to armature circuit, this field current will develop a flux known as a field flux. That field flux will induce an EMF in the armature winding. We call it as field induced EMF. Okay. And the armature winding will have some resistance, that is RA. Will have a synchronous reactance, that is XCS. And then finally we have supply source here, guys. Remember, it is a motor. Motor means the terminals are connected to a load or connected to a source. Connected to a source. Typically, that source is bus bar. Okay. So this is the supply source, and the source voltage is always at 0 degrees. Okay. Source means it is input side. Whereas for generator, this is load. Load means output side. Okay. But for motor, it is source, whereas it is input side. And a machine will now generate the current or absorb the current. Absorb the current, you see the direction of armature current. Armature current was taken by the machine. Okay, this is the direction of armature current, and the induced EMF is now lagging the terminal voltage by an angle delta. As it was lagging the voltage, that's why we are using a negative sign. So what are the important differences between generator circuit diagram and motor circuit diagram? In a generator, induced EMF is leading the terminal voltage by an angle delta, so it is a positive delta angle. But in motor, induced EMF is lagging the terminal voltage, therefore it is negative delta. Except that everything is same. The direction of armature current also reverses. So can we write down KVL equation in generator and motor? I will try to write down the KVL equation here. See, current was circulating in this manner. So current was flowing from EF to VT. Understand? Okay. So let us draw the KVL equation for generator and motor separately. Okay. KVL equation in case of a generator. Okay. We just understood that current was flowing from EF to VT. So start the equation from EF. All of you, please listen very carefully. Okay. Start from EF. So therefore, EF at an angle delta is equal to, yes, can I say when IA was flowing in this direction, drop will take place across ZS. Therefore, can I say IA into ZS is the voltage drop. So IA at an angle plus or minus phi, I will tell you what is phi, into ZS. ZS means, can I write RA plus JXS? Okay. RA plus JXS. Okay. After the drop across impedance, next drop is across load. What is the load voltage reference? VT at an angle 0 plus VT at an angle 0. This is the KVL equation for synchronous generator. Okay. If I write once again, EF at an angle delta is equal to, first let me write VT. VT at an angle 0 plus current. I have to represent everything in polar form here or rectangular form. Any one form you have to follow. See, current with power factor angle. Okay. So that phi is nothing but load power factor angle. Load power factor angle phi. And we know load may be a lagging power factor load or leading power factor load, or it may be unity power factor load also. Suppose if the load is a lagging power factor type, can I say armature current will lag the terminal voltage by some finite angle? Lagging means I have to use a positive angle or negative angle? Negative angle. Then in the KVL equation, this IA is at an angle minus phi, lagging power factor, into RA plus JXS. This is the equation for lagging power factor load. Okay. What if load is leading power factor type? Suppose if the load is leading power factor type, armature current will lead the terminal voltage by a power factor angle phi, then phi will be a positive angle. Okay. So therefore, EF at an angle delta is equal to VT at an angle 0 plus this armature current is at an angle plus phi into RA plus JXS. This is for a leading power factor load. So this is writing the KVL equation directly. Okay. So never write the KVL equation without showing angles. The common mistake students will do is they will write down the KVL equation without angles. That will work out only in DC circuits, not in AC circuits. In AC circuits, phase angles will play major role. Okay. Suppose if I say terminal voltage is equal to 200 volt, current is equal to 50 ampere, resistance is 1 ohm, reactance is 10 ohm. Find EF if I ask you. Will you write down, sir, EF is equal to VT plus IA into ZS. So VT is 200, IA is 50 ampere, ZS means 1 plus J10. Is it a correct equation? Wrong. Why this is wrong? Because you are not using angles properly. Okay, the exact equation is, yes, you have to write down EF is equal to, yes, VT 200 at an angle 0 plus armature current 50 ampere. 50 at power factor angle is important. That power factor angle is very important. Suppose if I say power factor is 0.8 lagging power factor, for example. What is meant by 0.8 lagging? Power factor will be 36.86 degrees lagging. Then this is 50 at an angle minus 36.86 degrees into 1 plus J10. This is writing the equation in a correct format. Alright. So the phase angles are extremely important. But the disadvantage of this equation is, especially when you are using GATE calculator, you know, in GATE calculator, complex mode will not be available. When complex mode is not available, solving such type of vector calculation becomes very difficult, also very lengthy. Then you have to divide everything into real part, imaginary part, multiply. It will increase the calculation length. That is why the wise decision is always solving these kind of KVL equations from the phasor diagram, the wise decision. From the phasor diagram, it will become much easier for you to solve such kind of equations. Okay, we will see phasor diagram also. Okay, anyway, this is the KVL equation for generator. Can I write down the KVL equation for motor? You may have a doubt, sir, what about unity power factor? Suppose if the load is unity power factor angle becomes 0. Understand? Okay, right. So let us write down the KVL equation for synchronous motor also. In synchronous motor. Okay, what is the only difference? Current direction. See that. In case of a motor, armature current was flowing from VT to EF. So start writing the equation from VT onwards. So VT is equal to, in the direction of the current, so VT at an angle 0 is equal to, yes, in the direction of the current, can I say first drop is along this impedance ZS. Therefore, IA plus or minus phi into ZS means RA plus JXS. After the drop in this impedance, can I say the next drop is this back EMF? Yes, we can call this EMF as back EMF also. Generally in motor, the induced EMF is known as back EMF or induced EMF, anything. So that is EF at an angle minus delta. Correct? So again, positive angle you have to use for leading power factor, negative angle you have to use for lagging power factor. So I take this drop to the left side. Let me write EF. So therefore, EF at an angle minus delta is equal to VT at an angle 0 minus IA at an angle plus or minus phi into RA plus JXS. Again, positive angle means the current is leading the terminal voltage. Negative angle means the current is lagging the terminal voltage. Okay, so that you can write down again the KVL equation. See, the difference is, in case of a generator, EF is at an angle plus delta, induced EMF is leading the terminal voltage. In case of a motor, induced EMF is lagging the terminal voltage, so this is at an angle minus delta. And in generator, EF is equal to VT plus the drop. In motor, EF is equal to VT minus the drop. Understand? Okay, because current direction reverses. So positive current becomes negative current. Clear? So this is the basic way of writing KVL equation in a synchronous generator as well as in a synchronous motor. But as I said, it will be a lengthy calculation if you do it in examination hall. So the best way is always solve the equations using, phasor diagram. If you are comfortable, okay, you can proceed. Otherwise, you better use phasor diagram. Okay. So that's why I would like to draw phasor diagram of alternator first, that is generator. Then I will draw phasor diagram of motor as well, so that you can compare both of them. Okay. In alternator, what is the KVL equation? Current direction is like this. EF is equal to VT plus this drop. Okay. Yes. EF is equal to Vt plus Ia into Ra plus Ia into Xs. See guys, I am already using a vector symbol here. That's why I am not showing you the angle. Without vector symbol, you can't write EF is equal to Vt plus Ia Ra plus Ia Xs. That becomes algebraic summation, which becomes wrong. Okay, I have already shown you all these are phasors. Clear? Okay. So, excuse me. So, let us draw the phasor diagram. To draw phasor diagram, I am considering a lagging power factor load. Okay, you can implement even for leading power factor and unity power factors as well. Okay, just a moment, guys. Okay, let's see the phasor diagram related to this KVL equation. See, what I am doing here is that I'll be taking terminal voltage as reference. Okay, so this is the terminal voltage at an angle 0. Reference means at an angle 0. Now, as I mentioned, lagging power factor load, the load current will lag the load voltage by a finite angle. This is the load voltage. Now, lagging means clockwise. So, the load current I is lagging the load voltage by a finite angle phi. Okay. Now, for this Vt, which drops we have to add to get EF? Yes, for this Vt, first I need to add Ia Ra drop. Ia Ra means Ra is a resistive parameter, right? In the circuit diagram, Ra is a resistance. So as it is resistance, can I say the voltage drop will be in phase with current? So this is Ia, therefore Ia Ra is also in phase with Ia. So draw that here. So this is Ia Ra drop. Okay. Generally, we will design armature winding to have a very low resistance to minimize the copper loss. That's why Ia Ra drop is also very small. Now the next one interesting thing, Ia Xs. What is meant by Xs? Remember, Xs is an inductive reactance. This is an inductive reactance. As Xs is an inductive reactance, Ia Xs is an inductor voltage. And we know in inductor, voltage will lead the current by 90. So therefore, this is current. Now Ia Xs will lead this current by 90. Leading means anti-clockwise by 90 degrees. Draw that here. This is Ia Xs. Now the sum, okay, Vt plus Ia Ra plus Ia Xs, the summation is what we call it as induced EMF. That is what the phasor diagram is. And the angle between this EF and Vt is what we call it as load angle delta. Understand? Okay. So therefore the observation is induced EMF EF is leading the terminal voltage by an angle delta. Also, you can understand there is an angle between induced EMF and armature current. We call it as internal power factor angle psi. Okay. Remember, from the circuit diagram, internal voltage is EF, current is Ia. Okay, the angle between internal voltage and internal current we call it as internal power factor angle psi. Okay, and this is the phasor diagram for which power factor? Lagging power factor. You can also draw the similar type of phasor diagram for leading power factor as well. Now, what I would like to do here is that I wanted to develop a formula. For that purpose, let us extend this Ia phasor a bit. Also extend this Ia Xs phasor. There will be 90 degrees, correct? And you also try to do one more thing. You just draw a parallel line. Okay, this line and this line both are parallel, so this is also 90 degrees. Now we know this gap, right? This is Ia Ra drop. That means, can I say this gap is also Ia Ra? This is also Ia Ra, correct? Next, are you finding a right angular triangle here? In this right angular triangle, what is this angle? Phi. If this is phi, can I say this is adjacent side of phi in this right angular triangle? So this side will become Vt cos phi. This length. This is Vt cos phi. Similarly, for this phi, exactly opposite side, this length, that is Vt sin phi. This length, Vt sin phi. If this is Vt sin phi, this is also Vt sin phi. Understand? Okay, already this length is IAXS. Okay, then what is the whole length? This total length, if you calculate, VT sin phi plus IAXS. What is this length? VT cos phi plus IARA. Then you look at this entire right angular triangle. This is looking like a hypotenuse EF. So one side VT cos phi plus IARA, other side VT sin phi plus IAXS. Therefore, what is the length EF is equal to? So you can write EF is equal to square root of, yes, one side VT cos phi plus IARA, VT cos phi plus IARA whole square. The other side, the opposite side, VT sin phi plus IAXS. VT sin phi plus IAXS whole square. So if you use this formula, vector calculations are not required. You can directly get the answer for induced EMF magnitude. Okay, so for that purpose you need VT cos phi IARA, VT sin phi IAXS. Here important thing is cos phi is the load power factor. And one more observation is, this is the phasor diagram that I have drawn for which power factor? Lagging power factor. If it is leading power factor, you will get a similar phasor diagram. Only one modification will happen in the equation. This plus IAXS becomes minus IAXS. I am not drawing the diagram once again. I hope you can perform that leading power factor, but I can write down the equation directly. There is only one modification. Instead of plus IAXS, we will get minus IAXS when it is leading power factor load. So therefore, when should I use plus sign here? When should I use minus sign? Positive sign we have to use for lagging power factor load. Negative sign we have to use for leading power factor load. Okay, remaining equation is as it is. Understand? Okay, so this is the formula to calculate induced EMF magnitude. Okay, and one more important equation from the phasor diagram is finding this angle psi. Very important. Finding this angle psi. So to find this internal power factor angle psi, I will apply, look at this entire right angular triangle, this big right angular triangle, apply tan psi concept. In a right angular triangle, tan of the angle will be opposite side by adjacent side. So what is a tan psi? Another important formula. Tan psi, where psi is known as internal power factor angle. Yes. Tan psi is equal to opposite side. What is the opposite side for this big right angular triangle? VT sin phi plus IAXS. VT sin phi plus IAXS divided by what is the adjacent side for this psi? For this psi, it is nothing but the adjacent side. VT cos phi plus IARA. VT cos phi plus IARA. So if you have this formula with you, you can find out psi. Now, if you know psi value and power factor angle phi value, can you find out the load angle delta? Yes, easily. So can I say delta is equal to psi minus phi simply? Also, if you implement the same phasor diagram for a leading power factor, then what will be the formula for psi? Yes, very simple. Instead of plus IAXS, you will get minus IAXS. That's it. This sign will not change, only this sign will change. So when should I use a positive sign here and when should I use negative? Positive for lagging power factor, negative for leading power factor. Okay, clear? So that is about internal power factor angle psi. This is everything for generator. Okay, now we will try to do the same analysis in synchronous motor also. Okay, so that you can have a clarity about the difference between generator and motor. Even though without drawing the diagram also, you can try to develop these equations in motor. What is the only difference between generator and motor? Direction of current flow. Therefore, in generator, if the current is positive, in a motor, it becomes negative. In a generator, if the current is negative, in a motor, the current becomes positive. So just the current sign will change from generating machine to motoring machine. So if this is the formula for synchronous generator, what about synchronous motor? Simple. Plus IARA becomes minus IARA. Plus IAXS becomes minus IAXS. Minus IAXS becomes plus IAXS. That is a shortcut way to remember the formula. But we will try to prove it by drawing a phasor diagram. Okay, so let us see phasor diagram in case of a synchronous motor. Understand? First, what is a KVL equation? In KVL equation, current will flow from Vt to EF. Therefore, EF is equal to, or EF is equal to Vt minus IaRa plus IaXs. This is one formula you can use, or Vt is equal to EF plus IaRa plus IaXs. Any formula you can implement. Now let me try to draw the phasor diagram. Once again, I am taking terminal voltage as reference. Now I would like to draw the phasor diagram in case of motoring machine for leading power factor. You can draw for lagging power factor also, no problem. When I say power factor is leading, armature current was leading the terminal voltage by an angle phi. And what is the first drop we wanted to draw? IaRa drop. Okay, we all know IaRa is nothing but resistance drop. Resistance drop is always in phase with current. What is the next one? IaXs drop. XS is an inductive reactance. Remember, the circuit diagram is like this. EF at an angle minus delta. This is Ra. This is XS. Okay. This is the terminal voltage. Vt at an angle 0. Okay. So, don't confuse. Sorry, you said leading power factor. So, XS is capacitive reactance. That is wrong. Okay. XS is nothing but a parameter which is internal to the machine. It's a machine parameter. And machine parameter is always an inductive reactance only. So, XS is an inductive reactance. If it is inductive reactance, can I say the voltage will lead the current by 90 degrees? This is current, guys. IaXs should lead this current by 90 and draw that IaXs below this Vt. This is IaXs. Why I am drawing it below Vt rather than above Vt? Because the rule is IaXs drop must be added to EF, not to Vt. I repeat, IaXs drop should be added to EF. Don't add to Vt. Suppose if I draw this IaXs drop above this Vt, that means you are adding the drop to Vt. But the rule is we should add the drop to EF. That's why draw it on the bottom side of Vt. Next, let us draw IaRa drop also in phase with current. Let us draw IaRa. 1 second, guys. This is IaXs anyway. Okay, next IaRa drop in phase with Ia. Let us draw here. Yes, this is IaRa. Now this gap is EF. Okay, and this is delta. You can understand now induced EMF is lagging the terminal voltage by an angle delta. And this is the internal power factor angle. We know as usually the angle between EF and Ia is the internal power factor angle. Okay, and if you extend the same phasor diagram, okay, so just extend this Ia phasor, also extend this IaXs phasor, it will make 90 degrees. Draw a parallel line here such that this is also making 90 degrees. Finally, you can develop the formula for EF. Okay, I don't want to derive it. I will directly write down what is the only difference. This plus sign becomes minus. Exactly, current will reverse and you can prove it. Okay, from this phasor diagram you can prove it. This is IaRa, this is also IaRa. You can try and you can try to prove it. Okay, yes. So, the formula for EF in case of synchronous motor is same formula, square root of Vt cos phi plus IaRa becomes minus IaRa, Vt sin phi plus or minus IaXs. And when we use plus sign here, in case of generator, plus is for lagging power factor, minus is for leading power factor. That is exactly opposite in motor now. Plus is for leading power factor, minus is for lagging power factor. Okay, exactly opposite to generator. Also tan psi formula. What is tan psi? Same formula like previous case. Vt sin phi plus or minus IAXS divided by VT cos phi minus IARA. Once again, plus is the sign we will use for leading, minus is the sign we will use for lagging. This is a simple formula, two formulas you need to remember so that you can answer any question related to phasor diagrams. Okay, fine. But one small confusion that every student has to avoid, that is relation among these three values, guys. Relation among power factor angle phi, load angle delta, internal power factor angle psi, that we wanted to avoid. So to avoid the confusion, I will consider a generator with all possible power factors, then we will consider motor with all possible power factors, then we will solve questions related to these concepts. Okay, see this. Consider a generating machine, generator. I will consider lagging power factor first. Okay, always take VT as reference. Next, where is armature current? I said lagging power factor. So armature current was lagging the terminal voltage by a power factor angle phi. Next, where is EF? I said the machine is a generator. Please, very important this is. In a generator, induced EMF will always lead the terminal voltage by an angle delta. Got it? Okay. Next, what is the angle between EF and IA? That is where internal power factor angle psi will come. And you can calculate this psi using tan psi formula. That is what we derived already. This is the relation among the three angles. Now I think you can easily relate, right? Psi is equal to delta plus phi. Delta is equal to psi minus phi. Simple. But the confusion will come at leading power factor. Generator with leading power factor. Okay. Yes. Let us first take terminal voltage. Terminal voltage is always the reference. Then where is armature current? I said leading power factor, therefore armature current will lead the terminal voltage. Okay, armature current will lead the terminal voltage phi. Then what about induced EMF? We know in a generator, induced EMF will lead the terminal voltage by a load angle delta. Here I am taking induced EMF, leading the terminal voltage by delta. And now you please try to understand one thing from the phasor diagram. The armature current was leading, definitely leading power factor. It is leading VT only or EF also. From the diagram, what is your opinion? Armature current was leading the terminal voltage and also leading the induced EMF. Okay. So this is a psi, internal power factor angle psi. And that psi you can find out from tan psi formula. What is tan psi formula? VT sin phi. Okay. Leading power factor minus IAXS divided by VT cos phi plus IARA. But there is another way to draw the phasor diagram. There is one more possibility is there. You look at the other possibility. Okay. So now VT I am taking as reference. As it is a leading power factor, armature current will lead the terminal voltage. But imagine power factor angle was very small. Let's say 10 degrees leading only. Armature current was leading the terminal voltage by a power factor angle phi. Why it was leading by small angle? Because I said very small leading power factor. Now, where is induced EMF? We know induced EMF will always lead the terminal voltage by a load angle delta. So let's say induced EMF is here. It is leading the terminal voltage by a load angle delta. Got it? But now you can understand the difference between the previous diagram and present diagram. In the present diagram, armature current was leading the terminal voltage, that is fine, but it is lagging the induced EMF. As it was lagging the induced EMF, internal power factor will become lagging power factor, correct? Okay. Whereas here, armature current was leading the terminal voltage and also leading the induced EMF. But here, it is leading the terminal voltage but lagging the induced EMF. Okay. So how do you recognize which is correct out of these two in a given problem? When a numerical question was given, How do you know whether armature current is leading both EMFs or it is only leading VT and lagging EF? How do you recognize? Very simple. You calculate this tan psi formula. Remember, this tan psi formula was derived considering current was leading both EMF phasors. Okay, when I derived this formula tan psi using a leading power factor, the assumption is not only load power factor, internal power factor is also leading. That is the assumption with which this formula was derived. Therefore, you are using this formula means your assumption is first diagram. Okay, but second diagram may also be possible. It depends upon the power factor angle. If the power factor angle was very small, this is also possibility. Yes. In that case, if you use the same formula, what happens? You will get psi a negative value. Okay. If this is the case, calculation of this tan psi will give you a psi positive angle. Okay, 15 degrees, 20 degrees, positive angle will come. When psi is positive, that means armature current is not only leading VT, it is also leading induced EMF. But when you use this formula, if psi turns out to be negative, that means armature current was leading terminal voltage, but it was lagging induced EMF. Okay, so then only you will be able to relate these three angles clearly. Suppose if a first case is followed, tell me what is a load angle delta. Can I say delta is equal to phi minus psi? Yes. If you use a second formula or second case, what is the delta formula? Delta is equal to phi plus psi. Okay. Which formula to be used? How do you know? Simple. Calculate tan psi. If psi turns out to be positive, that means armature current was leading terminal voltage as well as induced EMF. If psi turns out to be negative, that means armature current was leading VT but lagging EF. But remember, this formula was derived by assuming that armature current was leading both EMFs by finite angle. Okay. Now we will try to answer one question related to this concept. Okay. So just a moment. Okay. Just let me add the question. Okay. All of you look at this question. A 1000 kVA, 6.6 kV, 3-phase star connected cylindrical pole synchronous generator has a synchronous reactance of 20 ohm. Neglect the armature resistance and consider operation at full load and unity power factor. What is the induced EMF and also what is the torque angle? Okay, problem is easy. Why? Because it is given a unity power factor. Okay, unity power factor. Next important information, it is a synchronous generator. Synchronous reactance was given, excess value was given. Neglect armature resistance, that was clearly mentioned. And this 6.6 kV by default, it is line voltage. In a 3-phase system, by default given voltage is always line voltage. Also the machine is at full load, and what is the power at full load? 1000 kVA. That is the rated power. Output always, remember, nameplate will always give you output power of the machine only. So what is the induced EMF? Line to line. Also what is the power angle or torque angle? That is delta. Okay, so first let me try to calculate the current using power and voltage. Okay, so therefore the terminal voltage is equal to 6600 per line. That means what is per phase? 6600 by root 3 volt per phase. Okay, let me use my calculator and I will try to simplify this. Okay, so 6600 by root 3. So it will become 3810.55 volt per phase. It is a star connected circuit. Okay. Okay. So next, what is the power rating given? 1000 kVA. This is three-phase power. So by default, the volt ampere power three-phase is two formulas you can write: root 3 VL IL or 3 V phase I phase. Any formula you can use. I will use the first formula. So 1000 kVA, that is 1000 into 10 power 3, is equal to root 3 into what is the line voltage? 6600. I don't know what is the line current. That is what I wanted to calculate. So therefore, the line current you can calculate. So let me do it. 1000 into 10 power 3 divided by 6600 divided by root 3. So I'm getting 87.47 ampere. This is a line current, guys. If you know line current, then what is a phase current? Same value. Why? Because the given circuit is a star connection. Therefore, the phase current is also 87.47 ampere per phase. Correct? Okay. So now that I got current value, voltage value, everything, and what is the power factor given? Unity power factor, that is cos phi was also given. So first calculate what is the induced EMF per phase. Yes. What is the formula for induced EMF? Induced EMF is equal to square root of Vt cos phi plus IaRa. Remember, it is a generator, plus Vt sin phi plus or minus IaXs whole square. This is the formula for induced EMF. But fortunately in the question, what is the power factor? Unity. Unity power factor means cos phi is equal to 1. If cos phi is equal to 1, can I say sin phi will be equal to 0? Okay. Therefore, already Ra drop is neglected. Okay. Ra was not given. Ra is 0. Therefore, in the first term, only Vt remains. So, square root of Vt square plus sin phi is equal to 0. Therefore, remaining value IaXs whole square. Now, square root of what is Vt? Use phase values only. 3810.55. 3810.55 square. What is armature current we got? Please remember, guys, I am also using calculator just like you. If I made any mathematical mistakes, please try to correct them. Okay, but the procedure you need to follow. 87.47 current value into what is the reactance given in the problem? Yes, the reactance value was 20 ohm. Okay, 20 whole square. And if you solve this, you will get the induced EMF per phase. Okay, so let me do it. Okay, I'm getting 4192.99 volt per phase. Okay, per phase. But the question is to calculate phase voltage or line voltage. Line voltage we are asked to calculate. Okay, so therefore, the line voltage, induced EMF, line voltage will be equal to root 3 times of induced EMF per phase because it is star connection. So root 3 into what is the phase voltage? 4192.99. You will get line voltage. So root 3 into 4192.99. So I'm getting 7262.47. This is the volt per line, and you can convert into kilovolt now. 7.26 kilovolt. 7.26 kilovolt. That means the second option. Okay, second option. Clear? So this is about the induced EMF line to line for a unity power factor load. See, you can suppose if the question is a multiple choice type question, you can also try to answer without using a calculator as well. Because the terminal voltage is 6.6 kV. This is the induced EMF, guys. This is the resistance and this is the reactance. Okay, and this is the terminal voltage. Okay, now as the line voltage was already 6.6 kV, what will be the induced EMF? This is 6.6 kV, guys. Any power factor, we know resistance and leakage reactance will offer a drop in voltage only. I am neglecting armature reaction drop because at lagging power factor, armature reaction will give you drop in voltage. Leading power factor, it will give you rise in voltage, but at unity power factor, no effect of armature reaction. But leakage and resistance will always give you drop in voltage only. If this is a drop, can I say EF should be more than 6.6 kV? Then only KVL equation will satisfy. So the answer is induced EMF more than 6.6 kV. More than 6.6 kV means 5.5 kV is ruled out and 7.2 is the nearest value for 6.6 kV but more than 6.6 kV. That is one way. But if it is a numerical answer type, you must solve it to answer the problem. Okay? Yes. Now what is the next way? Next question, what is the power angle? Delta also you need to calculate. How could you calculate delta? Yes, calculate tan psi first. Okay? Or else use phasor diagram. This is VT. Okay? VT at an angle 0. VT at an angle 0. Now unity power factor, therefore IA is in phase with VT. RA drop is already neglected, so we have excess drop only. Therefore IA excess will lead IA by 90 degrees and this is induced EMF. Can I say this is the phasor diagram using unity power factor condition? Yes. Now you can calculate, you know, this is a psi as well. Okay, this is a psi as well. Why? Because angle between EF and VT, that is psi. So you can directly calculate tan psi is equal to opposite side IAXS by adjacent side VT. And psi is nothing but delta right now. Suppose if this idea doesn't touch your brain, at least you know standard formula for tan psi, right? What is a tan psi standard formula in case of generator? VT sin phi plus or minus IAXS divided by VT cos phi plus IA RA. RA drop is already neglected in the problem, so this is 0. Unity power factor cos phi is 1. Cos phi 1 means sin phi is 0. Therefore, the remaining value tan psi is use plus sign. Okay, IAXS. You have to use minus sign only for leading power factor divided by VT. Is this formula and the previous formula both are same only? So in the question, what is IA value we got? IA value was 87.47. 87.47 into XS 20 divided by VT 3810.55. Okay, so this will give you psi and delta both are same right now. Okay, so let me calculate. So 87.47 into 20 divided by 3810.55, tan inverse of that value. So I am getting 24.65 degrees. If this is internal power factor angle psi, load angle delta is also same because unity power factor. Okay, so it is 24.65. This is the answer. It's a common data type question. It was given for 2 marks in GATE 2005 exam. Okay, 2 marks questions actually. All right, so now we will try to answer one more question related to phasor diagram of a synchronous machine. Okay, let's see one more problem related to phasor diagram. Okay, so read the problem. This is a question in GATE 2008 exam. This is also a 2 marks question. A synchronous motor is connected to an infinite bus bar at 1 per unit voltage. drawing 0.6 per unit current at unity power factor. Its synchronous reactance is 1 per unit, resistance is negligible. What is the excitation voltage and also the load angle of the machine? Okay, so this time the question is from synchronous motor. Okay, the question is from synchronous motor. See, okay, all the values are in per unit values. Machine was connected to infinite bus voltage 1 per unit. That means the terminal voltage of the motor is 1 per unit, and it is drawing 0.6 per unit current. Okay, therefore armature current was 0.6 per unit, and unity power factor. Unity power factor, that means cos phi is equal to 1, so sin phi is equal to 0. Okay, once again the reactance was given 1 per unit. Okay, excess value was given 1 per unit. No information about resistance, so resistance is negligible. Even if this word is not given, you can neglect RA if it was not given in the problem. Okay, yes, so RA is neglected. Now what we need to calculate? First we need to calculate excitation EMF, and then we have to calculate the load angle. Yes, what is the formula for excitation EMF in case of a synchronous motor? Okay, so the induced EMF formula in motor is square root of Vt cos phi minus Ia Ra whole square plus Vt sin phi plus or minus Ia XS whole square. Now here plus per unit value, there is no difference between line and phase values now. So plus I have to use for leading power factor, minus I have to use for lagging power factor. At unity power factor, there is nothing called plus and minus because sin phi is 0, right? Cos phi is equal to 1. So RA is already neglected. So it is square root of the leftover term is Vt square in the first term, and whether it is plus or minus, actually you have to use plus only, plus or minus IAXS whole square. No confusion. Okay, so in the given question, Vt was 1 per unit, so 1 square plus Ia was 0.6, the current, if I am not wrong, yes, Ia is 0.6, XS is 1 whole square. Now find out the answer. Okay, so it is 1 plus 0.6 square, 0.36, so 1.36. 1.36 under square root, I am getting 1.16. This is the value of induced EMF, 1.16 or 1.17, nearest either C or D we have to identify based on the value of load angle. Okay, see, load angle is also same in both options, so you need not to calculate again. But whether it is leading or lagging, you have to answer yes. We know it is a synchronous motor. Synchronous motor means induced EMF will always lag the terminal voltage, therefore lagging is correct. Okay, so let us try to prove this angle as well, delta. To calculate delta, you first calculate what is psi. What is the formula for tan psi? Vt sin phi plus or minus IAXS divided by Vt cos phi minus Ia Ra. Here Ra is neglected, 0. Cos phi is unity power factor 1, sin phi is 0, and use a positive sign. Negative you need to use only for lagging power factor. So tan psi is equal to Ia. What is Ia? 0.6 XS 1 divided by Vt 1. So calculate psi now. So 0.6 by 1. Tan inverse 30.86, 30.96 degrees. If this is psi, how do you find out load angle delta? Draw the phasor diagram. This is Vt, guys, at an angle 0. Induced EMF will always lag the terminal voltage by an angle delta, correct? Because it is a motor. And where is armature current? As the power factor is unity. As the power factor is unity, armature current is always in phase with Vt. Okay. Now, what is the load angle? Load angle or internal power factor angle, both are same. Why? Because internal power factor angle means it is an angle between EF and IA. Correct? So right now psi and delta both are same, therefore the delta is also equal to 30.96 degrees lagging. Induced EMF phasor will always lag the terminal voltage by an angle delta. If it is generator, it will lead the terminal voltage. So therefore last option is correct. Simple question. Fine. So it's been more than 3 hours. Okay. So I would like to end the session here today. So I thought of completing synchronous machines in two parts, but I don't think it is possible. Okay, we have done only one third of the syllabus right now. So I will take another two sessions. Okay, one session I will discuss about characteristics and voltage regulation and types of excitations and power flow equations. One more session for parallel operation V and inverted V curves of generator and motor, etc. Okay, yes, synchronous condenser, everything. Okay, anyhow, now it's time for your questions. Okay, now I will go through the chat box and any questions if you have, I will try to give you the reply. Okay, you can post it. I will go through the chat box. Let's see some of the questions. All right, so I'm going through the chat box. Yeah, very good evening. Yeah, very good evening to everyone. Right. Um, yeah, I'll start induction machines and DC machines also once synchronous machines sessions are completed. Okay. Yeah. Any update about AP Transco AEE? Frankly speaking, I don't have any update regarding AP Transco AEE, but it's been more than 5 years that we don't have any notification from AP Transco. We can expect this year probably. Okay. All right. So Srinivas raised one question: why we are not using Faraday's law where EMF is minus n d phi by dt? Understand, minus n d phi by dt is the formula you can use when the flux is time varying in nature. Okay. But here in synchronous machine, we are using a time invariant magnetic field. So dynamically induced EMF will be produced, which is BLV sine theta. Okay. Any more questions, please let me know in the chat box. See, the schedule, I can't, tell you when exactly I'm going to consider or when exactly I'm going to take the session, because I have offline classes, okay, to be taken at the institute, and also I have online live classes as well. So I can't exactly tell you at what date I'll be going to take the class, but I'll definitely inform you at least 2 days prior to the schedule. Okay, you please subscribe to our channel. 2 days prior to the schedule, I will inform you, okay, about the session at least 2 days prior. So my aim was to complete synchronous machines in the next week. Okay, in the coming 1 week, by next Sunday I wanted to finish synchronous machines. Actually I thought of taking only 2 sessions. Okay, but I think in 2 sessions we will not be able to complete synchronous machines completely. I need at least 3 sessions, so one session completed today. So the 2 sessions I would like to finish by next Sunday. Weekly one machine I wanted to finish, so that by the end of December, you can consider that all the machines will be completed. Okay. So we are launching, few live courses also, especially crash course, those who wanted to prepare for GATE exam at the last minute. So I pinned the message in the chat box. You can go through that live course details once. Okay, that can definitely help you. Yes. Any more questions? Any more questions? Please let me know in the chat box. All right, that's all. Okay then, so we will conclude the session here today and we will meet in the next session again. Okay. Thank you so much. Good night.